Imagine a world where the ground beneath your feet isn't rock or soil, but diamond. Not scattered fragments or precious stones buried deep underground, but an entire planet, trillions upon trillions of tons of crystalline carbon, compressed under such unimaginable pressure that it has transformed into the hardest substance known to humanity. Now imagine that this planet is real. 40 light years from Earth, orbiting a star you can't see with the naked eye, there exists a world that defies everything we thought we knew about planetary formation. A world where the laws of chemistry and physics have conspired to create something that sounds like pure fantasy, but is absolutely undeniably real. This isn't science fiction, this isn't speculation, this is 55 Cancri e, a super-Earth exoplanet that scientists believe is composed primarily of diamond, a cosmic jewel larger than our own planet, worth more than every economy in human history combined, if we could ever reach it. But here's what will keep you watching. This planet shouldn't exist. The conditions that created it challenge our fundamental understanding of how worlds are born. And the deeper scientists dig into its mysteries, the more questions emerge. Questions that could reshape everything we think we know about the universe. How does a planet become diamond? What forces could create such an impossible world? And perhaps most intriguing of all, could there be more of them out there, glittering in the darkness, waiting to be found? Stay with me, because what you're about to discover will change the way you look at the night sky forever. Welcome back to the channel. If you're new here, you've just stumbled into one of the most extraordinary cosmic mysteries of our time. And if you're a regular viewer, thank you for joining me on another deep dive into the universe's most mind-bending phenomena. Today, we're embarking on a journey that will take us 40 light years from home to explore something that sounds impossible, a planet made almost entirely of diamond. But this isn't just another weird space fact video. This is a comprehensive exploration of how such a world could exist, why it challenges everything we thought we knew about planetary science, and what its existence means for our understanding of the cosmos. Over the next 2 hours, we're going to uncover the full story. We'll start with the moment astronomers first detected this impossible world, then dive deep into the science of how diamonds form, both here on Earth and in the crushing depths of an alien planet. We'll explore the theories, the debates, the controversies, and the implications that ripple out from this single discovery. This is the kind of video you can settle in with, let your mind wander through the cosmos, and come away with a completely new perspective on what's possible in our universe. Whether you're actively watching or letting it play while you work, study, or just contemplate the nature of reality, every chapter will reveal something that makes you stop and think. So grab a drink, get comfortable, and let's begin this journey together. Because the universe is stranger, more beautiful, and more astonishing than we ever dared imagine. Our story begins not with a telescope pointed at the stars, but with a question that has haunted humanity for millennia. Are we alone? But sometimes when you're searching for one answer, the universe gives you something completely unexpected. The year was 2004. The Hubble Space Telescope and ground-based observatories around the world were engaged in a systematic hunt for planets beyond our solar system, exoplanets. At that time, we'd only confirmed the existence of about 100 such worlds. Today, that number exceeds 5,000. But back then, every new discovery was groundbreaking. Astronomers were focused on a star called 55 Cancri, located in the constellation Cancer. You can't see it with your naked eye. It's too dim, requiring at least binoculars or a small telescope. But what makes this star fascinating isn't its brightness, it's what orbits around it. 55 Cancri is actually a binary star system, meaning two stars locked in a gravitational dance around each other. The primary star, 55 Cancri A, is similar to our Sun, slightly less massive, slightly cooler, but close enough that if you stood on a planet in its habitable zone, you'd see a familiar yellow sun in the sky. The companion star, 55 Cancri B, is a red dwarf, smaller and dimmer, orbiting at a distance. But it's what orbits 55 Cancri A that concerns us today, using a technique called radial velocity measurement, essentially detecting the tiny wobble a planet creates in its star's motion as it orbits. Astronomers detected not one, but multiple planets around this star. By 2004, they'd found 3. By 2007, 5 planets were confirmed, making 55 Cancri one of the first multi-planet systems ever discovered outside our solar system. The innermost of these planets, designated 55 Cancri, was detected in 2004. And from the very first observations, it was clear this world was strange. Let me paint a picture of what those first measurements revealed. 55 Cancri e orbits its star at a distance of just 2.3 million kilometers. To put that in perspective, Mercury, the closest planet to our Sun, orbits at about 58 million kilometers. This exoplanet is 25 times closer to its star than Mercury is to the Sun. At that distance, the planet completes one full orbit, aka its entire year, in just 18 hours. Think about that. 18 hours. You could watch the sunrise and sunset on this world multiple times in a single Earth day. The planet is orbiting so fast that if you were standing on its surface, you'd see its star racing across the sky. But the real shock came when scientists calculated the planet's mass and size. This wasn't a small, rocky world like Mercury. 55 Cancri e has about 8 times the mass of Earth and roughly twice Earth's radius. It's what astronomers call a super-Earth, a category of planet that doesn't exist in our solar system, something larger than Earth but smaller than Neptune. Now here's where things get interesting. When you know a planet's mass and size, you can calculate its density. Density tells you what a planet is made of. Low density suggests a gaseous world like Jupiter. High density indicates rock and metal like Earth or Mars. The initial density calculations for 55 Cancri e suggested something very dense, denser than Earth in fact. Scientists expected this planet to be made primarily of iron and silicate rocks, similar to our own world but compressed under its own massive gravity. But then came 2011 and everything changed. A team of researchers led by Yale astronomer Niku Madhusudan decided to take a closer look at this mysterious world. They gathered all the available data, the mass measurements, the radius calculations, the orbital characteristics, and built detailed computer models to figure out what this planet could actually be made of. Standard models suggested a planet with an iron core, a rocky mantle of silicate minerals, and maybe a thin atmosphere, similar to Earth's structure, just scaled up. But when Madhusudan's team ran the numbers, something didn't add up. The planet's density was too high for a standard rocky composition. Even accounting for the intense gravity compressing everything, the numbers suggested this world needed more heavy elements than a typical rocky planet would have, so they started experimenting with different compositions. What if the planet had more iron? The density still didn't quite match. What if it had different proportions of rock-forming minerals? Still not right. Then someone suggested something radical. What if this planet wasn't silicate-based at all? What if instead of being made primarily of silicon and oxygen like Earth's rocks, it was made primarily of carbon? The idea wasn't completely crazy. We know carbon is abundant in the universe. It's the 4th most common element in the cosmos, after hydrogen, helium, and oxygen. We've found carbon compounds everywhere we look, in interstellar clouds, in meteorites, in the atmospheres of other planets. Here on Earth, carbon forms the basis of all life and creates substances ranging from soft graphite to the hardest natural material known, diamond. The only difference between graphite and diamond is pressure and arrangement. Subject carbon to enough pressure and heat, and its atoms locked together in a crystal lattice so strong that nothing can scratch it. So the question became, could an entire planet be made primarily of carbon? And if so, what would happen to that carbon under the immense pressures inside a super-Earth? Madhusudan's team ran the calculations. They modeled the planet where carbon, not silicon, was the dominant element. A planet where instead of silicate rocks, you had various forms of carbon. And when they factored in the crushing pressures that would exist in such a planet's interior, pressures millions of times greater than Earth's atmosphere, something extraordinary emerged from the mathematics. At those pressures, carbon wouldn't remain in its soft graphite form. It would transform. It would crystallize. It would become diamond. Not just pockets of diamond like we find deep in Earth's mantle. not just a diamond-rich layer, but potentially an entire planetary layer, maybe even comprising a third of the planet's mass, made of solid, crystalline diamond. When the team published their findings in 2011, the response was immediate and intense. Headlines around the world proclaimed the discovery of a diamond planet. Scientists debated the findings. Skeptics questioned the assumptions. But the mathematics was sound, the physics was solid, and the implications were staggering. If Madhusudan was right, then 40 light years from Earth, there existed a world containing more diamond than any human had ever dreamed of. A planet where the mantle, the thick layer between the core and the crust, wasn't made of hot, flowing rock, but of diamond compressed into a solid, crystalline form. To understand just how much diamond we're talking about, let's do some quick math. 55 Cancri E has about 8 times Earth's mass. If roughly a third of that mass is diamond, as the model suggested, that's about 2.5 Earth masses of pure diamond. In more familiar terms, that's approximately 15 nonillion carats. That's 15 followed by 30 zeros. If you tried to calculate the value of that much diamond at Earth prices, you'd need to invent new words for numbers. The entire global economy, every asset, every currency, every resource on Earth doesn't even come close. This single planet contains more wealth than humanity could accumulate in 1 trillion years. But of course, the value isn't the point. What matters is what this discovery tells us about the universe. Because if one planet can be made primarily of diamond, how many more are out there? What other impossible worlds are waiting to be found? And perhaps most intriguingly, how does a planet like this form in the first place? That question would launch years of research, debate, and some surprising discoveries. But before we can understand how a diamond planet forms, we need to understand something more fundamental. How do diamonds form at all? To understand how an entire planet could be made of diamond, we need to start with something much smaller, a single carbon atom. Carbon is element number 6 on the periodic table. Every atom of carbon has 6 protons in its nucleus, 6 neutrons in its most common form, and 6 electrons orbiting around that nucleus. It's a simple atom, relatively light, and yet it's one of the most important elements in the universe. Why? Because carbon has a unique ability. It can bond with other atoms in an extraordinary variety of ways. Those 6 electrons orbiting the nucleus aren't arranged randomly. 4 of them occupy the outermost shell, and those 4 electrons can form bonds with other atoms. This might sound technical, but here's why it matters. Those 4 bonding sites mean carbon can connect with other atoms in countless configurations. It can form chains, rings, sheets, and 3-dimensional structures. It's the basis of all organic chemistry, all life as we know it, and also some of the most remarkable materials in nature. The same element, carbon, can exist in wildly different forms depending on how its atoms are arranged. This property is called allotropy, and carbon is the master of it. Take graphite, the soft dark material in your pencil. Graphite is pure carbon, but its atoms are arranged in flat sheets, like stacks of paper. Within each sheet, the atoms are strongly bonded, but the sheets themselves slide easily over one another. That's why graphite is slippery, why it makes a good lubricant, and why it leaves marks when you write with it. Now take diamond. Diamond is also pure carbon, chemically identical to graphite. But in diamond, each carbon atom is bonded to 4 other carbon atoms in a 3-dimensional tetrahedral structure. Every atom is locked in place, connected to its neighbors in all directions. This creates the strongest natural structure known to science. Same element, completely different properties. The only difference is arrangement. So what determines whether carbon becomes soft graphite or hard diamond? 2 things, pressure and temperature. And here on Earth, diamonds form deep underground. In the upper mantle, at depths of about 150 to 200 kilometers, at those depths, the pressure is around 50,000 to 60,000 times the pressure at Earth's surface. The temperature hovers around 1,000 to 1,200 degrees Celsius. Under those extreme conditions, carbon atoms don't have the freedom to arrange themselves into the loose sheets of graphite. The pressure literally forces them into the compact, three-dimensional structure of diamond. But there's a problem. Diamond forms in the mantle, but we find diamonds on the surface. How do they get here? The answer is volcanic violence. Every natural diamond you've ever seen came to the surface in a rare and powerful type of volcanic eruption. These eruptions are called kimberlite eruptions, named after Kimberley, South Africa, where they were first identified. Kimberlite eruptions are extraordinary events. They start deep in the mantle, where magma under intense pressure finds a weakness in the rock above. When that magma begins to rise, the pressure decreases. Gases dissolved in the magma, primarily carbon dioxide, start to bubble out, just like when you open a shaken bottle of soda. But this isn't a gentle fizz. As the magma rises and the gases expand, the eruption accelerates. By the time it reaches the surface, the magma is traveling faster than the speed of sound, blasting through the crust at supersonic velocity. It excavates a carrot-shaped pipe through the rock, carrying fragments of the mantle along with it. And in those mantle fragments, sometimes there are diamonds. The eruption is so fast, rising from depths of 150 kilometers in just a few hours, that the diamonds don't have time to transform back into graphite. They're frozen in their high-pressure form, preserved as they rise through the crust and erupt onto the surface. This is important for our story, because it tells us something crucial. Diamond is a high-pressure form of carbon. It's what carbon becomes when it's subjected to extreme force. Remove that pressure slowly, and diamond can revert to graphite, but keep it under pressure. Now bring it to the surface quickly, and diamond is stable. Now the pressure required to form diamond on Earth is about 50,000 times atmospheric pressure, or roughly 5 gigapascals if you want the technical term. That's immense by human standards. The deepest ocean trenches, the crushing depths at the bottom of the Mariana Trench, reach only about 1,000 times atmospheric pressure. But 5 gigapascals is nothing compared to what exists inside a planet like 55 Cancri. Remember, 55 Cancri is a super-Earth. It has 8 times Earth's mass packed into a sphere about twice Earth's radius. That means its interior is subjected to gravitational forces far exceeding anything we experience here. Let's think about what that means. Pressure in a planet's interior comes from the weight of all the material above pushing down. The more massive the planet, the more material there is and the more it weighs. But here's the key. Gravity increases with mass. So not only is there more material pressing down, but it's also being pulled harder. Scientists estimate that the pressure at the core of 55 Cancri E could reach hundreds of gigapascals, potentially over 1,000,000 times Earth's atmospheric pressure. Even halfway between the surface and core, the pressure would be tens of gigapascals. At those pressures, if carbon is present, it has no choice. It must become diamond. But here's where the story gets even more interesting. Diamond isn't the only high-pressure form of carbon. Scientists have discovered that if you subject carbon to even more extreme pressures, beyond what exists naturally on Earth, it can form other exotic structures. There's something called BC8 carbon, a bizarre crystalline form that only exists at pressures above 10 gigapascals. There's also theoretical predictions of metallic carbon, where the pressure is so extreme that carbon's electrons become delocalized and the material conducts electricity like a metal. We've never created these exotic forms in large quantities in the lab because sustaining such high pressures is incredibly difficult. But on a super Earth like 55 Cancri E, these pressures aren't just possible, they're inevitable. So when we say 55 Cancri E might be a diamond planet, we're simplifying. More accurately, it's probably a planet with different layers of carbon in different forms, all determined by the pressure and temperature at each depth. Near the surface, if there's carbon, it might exist as various carbon compounds, perhaps similar to organic materials or graphite. Deeper in, as pressure increases, those compounds would give way to pure diamond. Deeper still, the diamond might transition to more exotic high-pressure forms we've barely begun to understand. It's a layered world of carbon, each layer a different expression of the same element, shaped by the crushing weight of the planet above. Now let's pause for a moment and appreciate what this means. Every diamond you've ever seen, every engagement ring, every industrial cutting tool, every gemstone, formed at depths of 150 kilometers, under pressures of 50,000 atmospheres, carried to the surface by volcanic eruptions that happen maybe once every few million years. A single 1-carat diamond is considered valuable. A large diamond, even just a few carats, is rare enough to make headlines. But 55 Cancri E contains diamond not in carats, not in tons, not even in gigatons, but in planetary masses. Layers of it, potentially thousands of kilometers thick, existing in a state of permanent crystalline perfection under pressures we can barely imagine. It's difficult for the human mind to truly grasp the scale. If you could somehow mine this planet, extract its diamond, and bring it to Earth, you would crash not just the diamond market, but the concept of value itself. Diamond would become as common as sand. More common actually, because there'd be far more diamond than all the sand on all Earth's beaches combined. But of course we can mine it. At 40 light years away, 55 Cancri is far beyond our reach. With our current technology, traveling there would take hundreds of thousands of years. And even if we could reach it, the planet's surface conditions would vaporize any spacecraft we sent. Which brings us to an important question we haven't addressed yet. What is this planet actually like? We've talked about its composition, its interior, the diamond layers hidden beneath its surface. But what about the surface itself? If you could somehow survive on 55 Cancri, what would you see? The answer is both beautiful and terrifying. Remember, this planet orbits its star at just 2.3 million kilometers, so close that its year is only 18 hours long. At that distance, the star doesn't look like our Sun appears from Earth, a bright disk in the sky. It would dominate the entire sky, a vast hemisphere of burning gas filling your field of vision. The temperature on the day side of 55 Cancri reaches approximately 2,400 degrees Celsius. That's hot enough to melt most rocks. It's nearly as hot as Earth's mantle. The surface likely glows with its own heat, radiating in the infrared. At these temperatures, any atmosphere would be exotic. There's no water vapor, no nitrogen, no oxygen. Instead, astronomers detected what they believed to be a thin atmosphere of vaporized rock, silicates turned into gas by the extreme heat. Imagine standing on a world where the sky itself is made of vaporized stone, where pools of molten lava might flow across the surface, where any exposed carbon on the surface might not be diamond at all, but graphite or even sublimating into carbon vapor. The diamond, the unimaginable wealth of crystalline carbon, exists deep underground, protected from the surface inferno by layers of rock and metal. It's locked away in the planet's interior, preserved under pressure, forever beyond reach. But here's what keeps me up at night. We don't actually know for certain what the surface is like. Everything I just described is based on models, calculations, educated guesses. No human eye has ever seen 55 Cancri. No camera has ever photographed it directly. We infer its existence from the wobble it creates in its star's motion. We estimate its size from the tiny dimming of starlight when it passes in front of its star. We calculate its temperature based on its distance from that star. We model its interior based on its density. But we've never seen it. Not really, and that uncertainty, that gap between what we can calculate and what we can observe, is where the real mystery begins. Because some scientists aren't convinced 55 Cancri is a diamond planet at all. Some think the evidence has been misinterpreted. Others propose alternative explanations for its strange density and composition. The debate over what this world truly is and how it came to be has become one of the most fascinating controversies in modern astronomy. Let's take a step back and ask a fundamental question. Where does carbon come from? This might seem like an odd detour in our story about a diamond planet, but bear with me, because to understand how a planet could be made primarily of carbon, we first need to understand how carbon exists in the universe at all. The story begins not with planets, but with stars. When the universe began, about 13.8 billion years ago, it consisted almost entirely of hydrogen and helium. These are the lightest elements, hydrogen with 1 proton, helium with 2. The Big Bang created these elements in abundance, but created almost nothing else. For the first few 100 million years, the universe contained no carbon, no oxygen, no iron, no silicon. None of the elements that make up the rocky planets we know. None of the elements necessary for life. So where did they come from? The answer is stellar alchemy. Inside stars, hydrogen fuses into helium through nuclear fusion. This is what makes stars shine, what powers the sun. But in more massive stars, the fusion doesn't stop there. As a star ages and exhausts its hydrogen fuel, its core contracts and heats up. If the star is massive enough, the temperature rises high enough for helium fusion to begin. 3 helium nuclei can fuse together to form carbon, element number 6. This is called the triple alpha process, and it's how all the carbon in the universe was created. Every carbon atom in your body, in the air you breathe, in a diamond ring, in the graphite of a pencil, was forged in the heart of a star. But the process doesn't stop with carbon. In even more massive stars, carbon can fuse with helium to form oxygen. Oxygen can fuse to form neon and magnesium. The process continues, building heavier and heavier elements, all the way up to iron. When these massive stars finally exhaust their fuel, they explode as supernovae, scattering all those newly formed elements across space. These elements mix with interstellar gas clouds, and when those clouds collapse to form new stars and planets, they contain not just hydrogen and helium, but all the heavier elements created in previous generations of stars. This is why astronomers talk about stellar metallicity, not referring to actual metals, but to any element heavier than helium. A star's metallicity tells you how many heavy elements it contains, which in turn tells you something about its age and history. Our Sun is what astronomers call a population 1 star. It's relatively young, only about 4.6 billion years old, and it has relatively high metallicity. It formed from a gas cloud that had been enriched by multiple generations of previous stars. That's why the Sun's planetary system contains rocky planets like Earth, Mars, Venus, and Mercury. Now here's where it gets relevant to our story. The ratio of elements in a star's composition tends to reflect the ratio of elements in the planets that form around it. If a star is rich in oxygen and silicon, its planets will likely be silicate-based, with rocks made of silicon-oxygen compounds. If a star is relatively rich in carbon, its planets might incorporate more carbon compounds. Our Sun has more oxygen than carbon. The ratio is about 2 oxygen atoms for every carbon atom. That's why Earth is made primarily of silicates, rocks based on silicon and oxygen, with a relatively little carbon. But not all stars have this ratio. Some stars, particularly older stars or stars that formed from unusual gas clouds, can have different ratios. Some have more carbon than oxygen. These are called carbon-rich stars, and they're not uncommon in our galaxy. When a carbon-rich star forms a planetary system, the chemistry of those planets can be fundamentally different from our solar system. Think about it this way. When a planet forms, it's assembling itself from the material in the protoplanetary disk around the young star. That material contains various elements in various ratios. The elements don't exist in isolation. They bond with each other, forming compounds. In our solar system, oxygen was more abundant than carbon. So when planets formed, most of the carbon bonded with oxygen, forming carbon monoxide and carbon dioxide, gases that either escaped into space or ended up in planetary atmospheres. The oxygen that was left over bonded with silicon, forming silicates, the rocks that make up Earth's crust and mantle. But in a carbon-rich system, the chemistry is reversed. There's more carbon than oxygen, so all the oxygen bonds with carbon first, forming carbon monoxide and dioxide. But there's carbon left over, carbon that can't bond with oxygen, because there isn't enough oxygen to go around. That leftover carbon has to go somewhere. It can bond with other elements, forming various carbon compounds. Or, if conditions are right, it can exist as pure carbon, graphite, diamond, or other carbon forms. This means planets forming in a carbon-rich system could be fundamentally different from Earth. Instead of silicate rocks, you might have silicon carbide, a compound so hard it's used in industrial grinding tools. Instead of metal oxides, you might have metal carbides. And in the deep interior, where pressure is extreme, you might have vast amounts of pure carbon crystallized into diamond, This is the theoretical foundation for carbon planets, and it's why scientists took the idea of a diamond planet seriously. The chemistry is sound. The physics is solid. If a planet forms in a carbon-rich environment and has enough mass to generate the necessary interior pressures, diamond formation isn't just possible, it's inevitable. But there's a problem, and it's a big one. 55 Cancri, the star that 55 Cancri e orbits, isn't particularly carbon-rich. When astronomers measured the chemical composition of 55 Cancri A, the primary star, they found a fairly normal composition. The oxygen to carbon ratio is actually similar to our Sun's. There's slightly more oxygen than carbon, just like in our solar system. This creates a puzzle. If 55 Cancri isn't a carbon-rich star, why would one of its planets be a diamond world? One possibility is that the composition of the protoplanetary disk wasn't uniform. Maybe the region where 55 Cancri E formed happened to have a higher concentration of carbon compounds. Protoplanetary disks aren't perfectly mixed. They have variations in temperature, density, and composition at different distances from the star. It's possible that in the hot inner region where 55 Cancri E formed, certain carbon-rich compounds concentrated while oxygen-rich compounds were depleted. Perhaps those oxygen-rich compounds had already been incorporated into other planets, or had been driven outward by the star's radiation. Another possibility is that 55 Cancri E didn't form where it currently orbits. Many exoplanets, especially those in close orbits, are thought to have formed farther from their stars and then migrated inward. Perhaps 55 Cancri E formed in a region with different chemistry, accumulated carbon-rich materials, and then spiraled inward to its current position. Or maybe, and this is where some scientists become skeptical, maybe 55 Cancri E isn't a diamond planet at all. The evidence for the planet's carbon-rich composition rests primarily on one thing: its density. The mass and radius measurements indicate a density that's higher than a pure silicate planet would have. The diamond planet model explains this density by proposing a carbon-rich interior. But density alone doesn't uniquely determine composition. Different combinations of elements and compounds can produce the same overall density. You could potentially explain 55 Cancri E's density with other models. For instance, what if the planet has a larger iron core than initially assumed? Iron is denser than rock, so a planet with a bigger iron core would have higher overall density. Or what if the planet's interior is compressed more than standard models predict? Extreme temperatures or unusual internal structures could affect how the material is packed together. Some scientists have proposed alternative models where 55 Cancri E is a water world, a planet with a massive ocean or a thick layer of water and ice in high pressure forms. Under enough pressure, water can form into exotic ices that remain solid even at high temperatures. These high pressure ices are denser than normal water and could potentially explain the planet's density without requiring carbon. Others suggest the planet might be rich in graphite rather than diamond. Carbon in its low pressure form could be stable in certain regions of the planet, especially near the surface or in the outer mantle. The problem is, we can't simply look at the planet and see what it's made of. We're limited by distance and technology. All our conclusions are based on indirect measurements and theoretical models. And models, no matter how sophisticated, can be wrong. This uncertainty hasn't stopped the scientific debate. In fact, it's intensified it. Since the diamond planet hypothesis was first proposed in 2011, dozens of papers have been published, some supporting it, some challenging it, some proposing modifications and alternatives. One of the most significant challenges came from analyzing 55 Cancri E's atmosphere. In 2016, a team of astronomers used the Hubble Space Telescope to study the planet during transit, when it passes in front of its star from our perspective. By analyzing how starlight filters through the planet's atmosphere, they could identify what gases are present. They detected hydrogen and helium, which wasn't surprising, but they also found evidence of hydrogen cyanide, a carbon-nitrogen compound. The presence of hydrogen cyanide suggests the atmosphere is indeed rich in carbon compounds, which supports the carbon planet hypothesis. But the same observations revealed something unexpected. The atmosphere seems to contain more oxygen than a pure carbon planet would have. Specifically, there might be water vapor or carbon dioxide in the atmosphere. If the planet's interior is carbon-rich with little oxygen, where would atmospheric oxygen come from? One possibility is volcanic outgassing. The planet's interior might not be as carbon-dominated as the diamond planet model suggests, and volcanic eruptions could be releasing oxygen-bearing compounds into the atmosphere. Another possibility is that the atmosphere we're seeing doesn't reflect the bulk composition of the planet. Atmospheres can be replenished from space by comets delivering water, by stellar wind interactions, or by other processes that add elements not abundant in the planet's interior. The truth is, we don't know. And that uncertainty is both frustrating and thrilling, because it means the mystery is still unsolved. The question of what 55 Cancri air truly is remains open, and every new observation has the potential to revolutionize our understanding. But let's assume, for the sake of our exploration, that the diamond planet hypothesis is correct, or at least partially correct. Let's assume there is indeed a vast layer of crystalline carbon deep inside this world. That raises an even more intriguing question. How did it get there? How does a planet accumulate enough carbon to build a diamond mantle? To answer that, we need to go back to the very beginning. Back to the birth of planetary systems, to the swirling disk of gas and dust around a young star, where worlds are built from chaos. Picture a newborn star, just ignited, blazing in the darkness of space. Around it, stretching out millions of kilometers in all directions, is a disk, a protoplanetary disk, a vast swirling pancake of gas and dust left over from the star's formation. This disk is the birthplace of planets. And the story of how random specks of dust become worlds larger than Earth is one of the most remarkable tales in science. Let's start small. The protoplanetary disk contains gas, primarily hydrogen and helium, and dust. The dust particles are tiny, microscopic even, grains of various materials, silicates, tiny crystals of minerals, metal oxides, carbon compounds, ice particles. Each grain is smaller than the width of a human hair. These dust grains drift through the disk, occasionally bumping into each other. And when they do, something interesting happens. They stick. It's not gravity holding them together. Not yet. Gravity is far too weak at this scale. Instead, they stick through something called van der Waals forces, weak electromagnetic attractions between molecules. The same force that lets a gecko climb a wall lets dust grains cling together. Two grains collide and stick, forming a slightly larger particle. That particle collides with another and another. Slowly, grain by grain, these particles grow. From microscopic dust to sand-sized grains. From sand to pebbles. From pebbles to rocks. This process is called accretion. And in the early stages, it's gentle and gradual. But as the particles grow, something changes. They start to have enough mass that gravity becomes relevant. Once a clump of material reaches about 1 kilometer in size, we call these planetesimals, their gravity becomes strong enough to pull in nearby material more efficiently. They sweep up dust and smaller rocks as they orbit through the disk. The bigger they get, the more material they attract. Growth accelerates. Planetesimals collide with each other. Some collisions are gentle enough that the objects merge, combining their mass. Other collisions are violent, shattering both objects and sending fragments scattering. But statistically, the larger objects survive more often. Over time, the disk is dominated by fewer and fewer objects, each one growing larger. The rich get richer, gravitationally speaking. Eventually, a few planetesimals emerge as clear winners. These protoplanets have swept up most of the material in their orbital zones. They're massive enough that their gravity shapes them into spheres. They're starting to look like actual planets. But the process isn't over. These protoplanets can still collide with each other, creating catastrophic impacts that melt their surfaces, vaporize their atmospheres, and completely reshape them. Earth itself is thought to have formed from one such giant impact, when a Mars-sized protoplanet collided with the early Earth, splashing material into orbit that eventually became the Moon. This whole process from dust grain to planet takes time. Estimates suggest it requires several million to tens of millions of years. That sounds long, but remember, stars live for billions of years. Planetary formation is over in the blink of an eye on cosmic timescales. Now here's what's crucial for our story. What a planet is made of depends on where in the disk it forms. The protoplanetary disk isn't uniform. Temperature varies with distance from the star. Close to the star, the disk is hot, heated by the star's radiation and by the friction of material spiraling inward. Farther out, the disk is cold, barely warmed by the distant star. Temperature determines what materials can exist in solid form. This creates what astronomers call ice lines or snow lines, boundaries where specific compounds transition from gas to solid ice. Close to the star, inside the frost line, is too hot for water ice to exist. Water exists as vapor, drifting in the gas disk, unable to contribute to solid planetary growth. Only materials with high melting points, metals like iron, silicate minerals, can exist as solids. This is why the inner planets of our solar system, Mercury, Venus, Earth, Mars, are small, dense, and rocky. They formed inside the frost line, where only rock and metal could contribute to their growth. Beyond the frost line, the story changes. Water can condense into ice. And since oxygen is abundant, water ice is plentiful. This dramatically increases the amount of solid material available. Planets forming beyond the frost line can grow much larger, because they're accumulating not just rock and metal, but also vast amounts of ice. This is why the outer solar system has giant planets. Jupiter, Saturn, Uranus, Neptune, they all formed beyond the frost line where ice was available. They grew massive cores of rock, metal, and ice, and their gravity became strong enough to pull in enormous atmospheres of hydrogen and helium gas. But water isn't the only compound with an ice line. Carbon monoxide has its own, farther out. Ammonia has one. Carbon dioxide has one. Each compound freezes at a different temperature, creating a series of boundaries in the protoplanetary disk. The location where a planet forms determines what materials it can incorporate, and small differences in the disk's temperature or composition can lead to dramatically different planetary outcomes. Now let's bring this back to carbon planets. In a carbon-rich protoplanetary disk, one where carbon is more abundant than oxygen, the chemistry is fundamentally different. Remember, oxygen and carbon bond readily to form carbon monoxide and dioxide. In a carbon-rich environment, all the available oxygen gets locked up in these compounds with carbon. But there's carbon left over, carbon without oxygen to bond to. This free carbon can exist as various carbon compounds, hydrocarbons, organic molecules, soots, and tars. And in the solid form, it can exist as graphite or amorphous carbon. As planetesimals form in a carbon-rich disk, they incorporate these carbon compounds. A planet growing in such an environment would be building itself from carbon-rich materials rather than the oxygen-rich silicates that dominate our solar system. Over time, as the planet grows larger and its interior heats up from gravitational compression and radioactive decay, the carbon within it begins to separate and differentiate. Heavier materials sink toward the center. Lighter materials rise toward the surface. But carbon is tricky. Its density depends on its form. Diamond is denser than graphite. Silicon carbide has different density than pure carbon. The interior structure of a carbon planet might be complex, with different carbon-bearing minerals at different depths. And deep in the interior, where pressure is extreme, the carbon crystallizes into diamond. This is the theoretical pathway for diamond planet formation. It requires a carbon-rich protoplanetary disk, planet formation in the inner, hotter regions of that disk, and sufficient planetary mass to generate the pressures needed for diamond formation. But here's the fascinating part. This process might be more common than we initially thought. Recent studies of exoplanet statistics suggest that planetary systems come in a much wider variety than we see in our own solar system. There are hot Jupiters, gas giants orbiting close to their stars. There are super-Earths, rocky planets larger than Earth. There are mini-Neptunes, worlds too small to be Jupiters, but too large to be rocky. And importantly, the composition of these planets shows enormous variation. Some are clearly water-rich, others appear to be silicate-rich, and some, like 55 Cancri E, might be carbon-rich. The diversity suggests that protoplanetary disks can have a wide range of compositions, influenced by the star's metallicity, the history of the molecular cloud that formed the star, and perhaps even by nearby supernova that enriched the region with specific elements. In other words, carbon planets might not be rare oddities. They might be a natural outcome of planetary formation under certain conditions. But there's another pathway to creating a diamond planet, and it's even more dramatic. What if 55 Cancri E didn't form as a carbon-rich planet? What if it started as a gas giant, similar to Neptune or Uranus, with a rocky core and a massive atmosphere of hydrogen and helium? And then, what if something stripped away that atmosphere? At its current orbital distance, just 2.3 million kilometers from its star, 55 Cancri E is subjected to intense stellar radiation. The star's heat and stellar wind are constantly blasting the planet's dayside. For a gas giant, this is deadly. Hydrogen and helium are light gases, and they're easily heated by stellar radiation. The atmosphere expands, and the outermost layers can escape into space, blown away by the stellar wind. This process is called atmospheric stripping, or photoevaporation, and we've observed it happening to several hot Jupiters. Over millions of years, the planet's atmosphere can be completely removed, leaving behind only the dense, rocky or icy core. If 55 Cancri E was once a much larger planet with a thick atmosphere, and if that atmosphere was stripped away, we'd be left with the exposed core. And if that core was rich in carbon compounds, perhaps from ices that formed in a cooler region of the disk before the planet migrated inward, then we'd have a carbon-rich planet even without a carbon-rich protoplanetary disk. This scenario is speculative, but it's consistent with the evidence. Many close-in exoplanets are thought to have migrated from farther out, so the idea that 55 Cancri E didn't form in its current position isn't controversial. And if the planet did migrate inward, after forming with a carbon-rich core, the subsequent atmospheric stripping would reveal that core to our observations. There's even a third possibility, more exotic and uncertain. What if 55 Cancri E is the remnant of a stellar collision? Binary star systems sometimes undergo dramatic interactions. If two stars in a binary system orbit close enough, they can exchange material, or even merge. During such events, enormous amounts of gas and stellar material are ejected into space. Could a planet have formed from this ejected material? Could the unusual conditions of such an event create a carbon-rich environment? It's wildly speculative, and there's no direct evidence to support it, but it illustrates just how uncertain we still are about this world's origins. The truth is, we don't know which of these scenarios, if any, actually describes 55 Cancri E's formation. We have models, calculations, and educated guesses, but without being able to directly sample the planet's interior or observe its formation history, we're piecing together a puzzle with missing pieces. And yet, despite the uncertainty, the fact remains: this planet exists, whatever its origin, whatever its exact composition. 55 Cancri E is a world unlike any in our solar system, a world that challenges our assumptions and expands our understanding of what's possible. But the diamond planet isn't alone in challenging those assumptions, because as astronomers have continued to search for and study exoplanets, they've found other worlds that might be carbon-rich, other potential diamond planets lurking among the stars, and that raises a tantalizing question. Just how common are these cosmic jewels? 40 light-years away, 55 Cancri E glitters in the darkness. But is it alone, or are there other diamond worlds scattered throughout the galaxy, waiting to be discovered? To answer that question, we need to understand how astronomers find and study exoplanets in the first place. Because detecting a planet around another star isn't easy. Planets don't produce their own light. They shine only by reflecting light from their stars. And they're tiny compared to those stars, making them almost impossible to see directly. Imagine trying to spot a firefly next to a searchlight from hundreds of miles away. That's the challenge of directly imaging an exoplanet. So astronomers use indirect methods. The two most successful techniques are the transit method and the radial velocity method, and both played crucial roles in the discovery and characterization of 55 Cancri e. The transit method is conceptually simple. If a planet's orbit is aligned just right from our perspective, the planet will pass in front of its star as it orbits. When it does, it blocks a tiny fraction of the star's light. By measuring this dimming, usually less than 1%, we can detect the planet's presence. The amount of dimming tells us the planet's size. A bigger planet blocks more light. The frequency of the transits tells us the planet's orbital period, how long its year is. And by analyzing the starlight filtering through the planet's atmosphere during transit, we can identify what gases are present. NASA's Kepler Space Telescope used this method to discover thousands of exoplanets. It stared at a single patch of sky for years, continuously monitoring over 150,000 stars, looking for the telltale dimming that signals a planet crossing in front of its star. Cancri A was detected transiting its star, allowing astronomers to measure its radius precisely. At roughly twice Earth's radius, it's clearly larger than our planet. Combined with its mass, measured using the radial velocity method, this gives us its density. The radial velocity method is equally clever. As a planet orbits a star, it doesn't actually orbit around a stationary point. Both the planet and star orbit around their mutual center of mass. For a star with a planet, this center of mass is usually close to the star's center, but not exactly at it. This means the star wobbles slightly as the planet orbits. Sometimes the star is moving toward us, sometimes away. This motion causes the star's light to shift very slightly in wavelength, toward blue when approaching, toward red when receding. It's the Doppler effect, the same phenomenon that changes the pitch of a passing siren. By measuring these tiny wavelength shifts, astronomers can detect the star's wobble and infer the presence of a planet. The size of the wobble tells us the planet's mass. More massive planets create bigger wobbles. Combining transit and radial velocity measurements gives us both the planet's size and mass, which allows us to calculate density. And density is the key to understanding composition. This is how we know 55 Cancri e is unusually dense, and is how we've identified other potentially carbon-rich planets. One of the most intriguing candidates is WSP-12b, a gas giant orbiting a Sun-like star about 1,400 light-years away. WSP-12b is a hot Jupiter, a massive planet orbiting extremely close to its star, completing an orbit in just 1.1 days. In 2010, researchers analyzing WSP-12b's atmosphere detected something unexpected: a carbon-to-oxygen ratio greater than 1. In other words, more carbon than oxygen. This was the first time such a ratio had been measured in an exoplanet atmosphere, and it suggested the planet formed in a carbon-rich environment. If WSP-12b's atmosphere is carbon-rich, its interior might be as well. Being a gas giant, it doesn't have the solid diamond layers that a rocky planet like 55 Cancri e might have. But its solid core, buried beneath thousands of kilometers of hydrogen and helium atmosphere, could potentially be made of carbon compounds. Some models suggest WSP-12b's core might contain diamonds mixed with silicon carbide and other exotic carbon-bearing minerals. The core itself could be larger than Earth, meaning there could be more diamond in WSP-12b's core than in the entire mantle of 55 Cancri e. But again, we're limited by what we can observe. We can't see WSP-12b's core. We can only infer its composition from atmospheric measurements and models. Another candidate is 55 Cancri e's sibling, sort of. The 55 Cancri system has 5 known planets, and while the others aren't as close to the star or as dense as 55 Cancri e, they all form from the same protoplanetary disk. If that disk had carbon-rich regions, other planets in the system might also have elevated carbon content, though probably not to the same extreme degree. Then there's PSR J1719-1438b, which might be the most exotic diamond world of all because it's not orbiting a star, it's orbiting a pulsar. Pulsars are the collapsed cores of dead stars, spinning rapidly and emitting beams of radiation. PSR J1719-1438 is a millisecond pulsar, rotating over 170 times per second. And in 2011, astronomers discovered it has a companion, a planet with about the mass of Jupiter, orbiting at a distance closer than Mercury orbits the Sun. But this planet's density is extraordinary. It's far denser than any normal planet should be, with a density similar to diamond. The leading theory is that this object was once a massive star that formed a binary system with the star that became the pulsar. As the companion star evolved, it expanded into a red giant. The pulsar's gravity stripped away the companion's outer layers, leaving behind only the core. That core, composed primarily of carbon and oxygen, has been crystallized by immense pressure into a planet-sized diamond. Unlike 55 Cancri E or WST-12b, PSR J1719-1438b might not just have diamond layers, it might be almost entirely diamond. A Jupiter-mass diamond spinning around a dead star, the remnant of a cosmic catastrophe. It's a reminder that the universe's capacity for creating strange and wonderful things exceeds even our wildest imaginations. So how many diamond planets are out there? The honest answer is, we don't know. But we can make educated guesses based on what we've learned about planetary formation and stellar compositions. Studies of stars in our galaxy show that roughly 10 to 20% of Sun-like stars might have carbon to oxygen ratios close to 1 or higher. These stars are candidates for hosting carbon-rich planetary systems. If even a fraction of these stars have planets, and if some of those planets formed in the carbon-rich regions of their protoplanetary disks, there could be thousands, maybe millions, of carbon planets in our galaxy alone. Most of them wouldn't be pure diamond planets. Carbon can form many different compounds and structures, and not all carbon-rich planets would have the right conditions for extensive diamond formation. You need high pressure, which means you need sufficient planetary mass, you need a certain temperature range, you need the right chemical environment. But some planets, perhaps a few percent of carbon-rich worlds, might meet all these criteria. Super-Earths and mini-Neptunes with carbon-rich cores, subjected to immense internal pressures, could have substantial diamond layers. In a galaxy with hundreds of billions of stars, even a small percentage could mean millions of diamond planets. And that's just in the Milky Way. The observable universe contains at least 2 trillion galaxies. If our galaxy is typical, the total number of diamond planets in the observable universe could be measured in quintillions. Let that sink in. Quintillions of worlds scattered across the cosmos with interiors of crystalline carbon. More diamond than the human mind can comprehend, existing in a form we can never access. But here's what really captures my imagination. We've only just begun to look. Our exoplanet detection methods are still in their infancy. The first confirmed exoplanet around a Sun-like star was discovered in 1995, less than 30 years ago. We've gone from knowing of one planetary system, our own, to knowing of thousands in a single generation. And our tools are improving rapidly. New telescopes, both on the ground and in space, are pushing the boundaries of what we can detect and characterize. The James Webb Space Telescope, launched in 2021, has infrared capabilities that allow it to probe exoplanet atmospheres in unprecedented detail. Future missions will go further. Concepts for telescopes that could directly image rocky exoplanets are already in development. Within decades, we might be able to actually see worlds like 55 Cancri E, not as abstract measurements, but as real images. Imagine that moment. The first photograph of a diamond planet, not an artist's rendering, but an actual image captured by a telescope. A pale dot in the darkness, glinting with reflected starlight. What will we learn when that day comes? Will we confirm that 55 Cancri E is indeed rich in diamond? Or will we discover something even more exotic? Will we find that diamond planets are common or rare aberrations? And perhaps most intriguingly, will we find that some of these worlds have conditions we never anticipated? Conditions that might, against all odds, support forms of chemistry or even life that we never imagined possible. That last question might sound absurd. After all, 55 Cancri's surface is hot enough to melt rock. Its atmosphere is vaporized stone. It's tidally locked to its star, meaning one side eternally faces the inferno while the other is plunged into darkness. It's hardly a hospitable environment. But the universe has surprised us before. Life on Earth exists in environments we once thought impossible. In boiling acid springs, in the frozen Antarctic valleys, in the crushing depths of the ocean, where no light penetrates. Who's to say that on some carbon-rich world, under conditions we can't yet imagine, chemistry might find a way to create complexity? Not life as we know it, perhaps, but something else. Something based on different chemistry, different principles, different rules. It's speculation, of course. Wild speculation. But speculation rooted in the knowledge that the universe is stranger, more diverse and more creative than we've ever given it credit for. Because the diamond planet isn't just a curiosity. It's a window into possibilities. It's evidence that planetary formation can take paths we never predicted. It's a reminder that our solar system, with its neat arrangement of rocky inner planets and gassy outer giants, is just one example among countless variations. And if planets can be made of diamond, what else is possible? What other exotic worlds are waiting to be discovered? Let's dig deeper into the physics because there's something remarkable happening inside a diamond planet that deserves our full attention. Something that challenges not just our understanding of planets, but our understanding of matter itself. Pressure. We experience it every day without thinking about it. The weight of the atmosphere pressing down on us at sea level is about 14.7 pounds per square inch, or 1 atmosphere of pressure. It's enough to support a column of mercury 760 millimeters high, which is why we measure atmospheric pressure in millimeters of mercury. Go underwater and pressure increases. For every 10 meters you descend, you add another atmosphere of pressure. At the bottom of the Mariana Trench, the deepest point in Earth's oceans, the pressure reaches about 1,100 atmospheres, enough to crush most human-made submarines. But that's nothing compared to the pressures inside planets. At Earth's core, about 6,400 kilometers below the surface, the pressure reaches 3.6 million atmospheres, about 360 gigapascals in scientific units. That's the weight of everything above pressing down. The crust, the mantle, the outer core, all of it being pulled inward by Earth's gravity. Under these conditions, iron, which makes up most of Earth's core, isn't liquid like we normally think of liquids. It's not even solid like typical solids. It exists in a state of matter that doesn't occur anywhere on Earth's surface, with properties we're still working to understand. Now scale up to 55 Cancri e, 8 times Earth's mass but only twice the radius. That means the material is packed much more densely and the gravity at the surface is stronger, about twice Earth's surface gravity. But it's the interior pressure that's truly extreme. Calculations suggest the pressure at 55 Cancri e's core could exceed 700 gigapascals, nearly twice Earth's core pressure. Even halfway between the surface and core, the pressure would be around 100 gigapascals. To put that in perspective, 100 gigapascals is about 1 million atmospheres. It's the pressure you'd experience if you stacked the entire atmosphere of Earth on top of itself 1 million times. At these pressures, matter behaves in ways that seem almost magical. Chemical bonds that are stable at normal pressures break and reform in new configurations. Elements that don't normally react with each other suddenly become chemically active. Materials that are insulators at the surface become conductors in the deep interior. And carbon, wonderful, versatile carbon, transforms into diamond. But not just any diamond. The diamond we're familiar with, the kind in jewelry, forms at relatively modest pressures by planetary standards around 5 gigapascals. At higher pressures, diamond becomes even more compressed. The carbon atoms are forced closer together, making the crystal lattice even denser and stronger. At around 10 gigapascals, something interesting happens. The diamond structure begins to change. Scientists have discovered that at very high pressures, carbon can adopt different crystalline structures beyond the familiar cubic diamond we know. This hexagonal diamond, also called Lonsdaleite, where the atoms are arranged in a hexagonal pattern instead of cubic. This form of diamond is thought to form during meteorite impacts. When graphite is subjected to extreme shock pressures, it's even harder than cubic diamond. At pressures above 100 gigapascals, pressures that would exist in the deep interior of 55 Cancri E, carbon might form even more exotic structures. There are theoretical predictions of super hard carbon phases, with densities and hardness exceeding even Lonsdaleite. We've never created these materials in the lab because we can't sustain such high pressures in large volumes. Our most advanced diamond anvil cells, devices that squeeze tiny samples between diamond tips, can reach these pressures, but only for microscopic samples and brief moments. But inside a super Earth like 55 Cancri E, these pressures aren't fleeting. They're permanent, sustained by the immense mass of the planet itself. Trillions of tons of diamond, compressed into forms that have never been studied, with properties we can only guess at. Here's where it gets even more interesting. At extreme pressures, carbon doesn't just get harder. It might start conducting electricity. Normal diamond is an electrical insulator. That's because the electrons in the carbon atoms are all locked up in strong covalent bonds, holding the crystal together. There are no free electrons to carry electrical current, but squeeze diamond hard enough and the bonds begin to deform. The electron clouds around each atom are compressed, and at a certain point they start to overlap. Electrons can begin moving between atoms. The material transitions from an insulator to a conductor. This is called pressure-induced metallization, and it's been observed in several materials. Hydrogen, normally a gas or a liquid, becomes metallic at extreme pressures, possibly forming a metallic hydrogen layer in the interiors of Jupiter and Saturn. Scientists predict that carbon should also become metallic at extreme pressures, though the exact pressure required is still debated. Some models suggest it happens around 300 gigapascals, which would be deep in 55 Cancri E's interior. Other models predict higher or lower pressures. Well, if metallic carbon exists in 55 Cancri's core, it would have profound implications. Metallic layers in planets can generate magnetic fields through the dynamo effect, the same process that generates Earth's magnetic field. Could 55 Cancri E have a magnetic field powered by metallic carbon? We don't know. We've never detected a magnetic field around an exoplanet. They're too far away and too faint. But if such a field exists, it could shield the planet from some of the stellar radiation it's subjected to, possibly affecting the rate of atmospheric loss. There's another bizarre possibility. At pressures even higher than those required for metallization, carbon might undergo another transition. Some theoretical studies suggest that at pressures around 1000 gigapascals, which might exist in the cores of even larger super-Earths, carbon could become a superconductor. Superconductors are materials that conduct electricity with zero resistance. Electrons flow through them without losing energy. On Earth, superconductivity only occurs at extremely low temperatures, just a few degrees above absolute zero. But some materials, under high pressure, can become superconducting at higher temperatures. If carbon becomes superconducting under extreme pressure, and if some super-Earths have the right conditions, you could have planets with superconducting cores. Electric currents flowing through the core without resistance, potentially generating incredibly strong and stable magnetic fields. It's speculative, bordering on science fiction, but it's rooted in real physics, real equations, real predictions from quantum mechanics and solid-state physics. And it illustrates something crucial. We're not just talking about a planet made of pretty gemstones. We're talking about matter in extreme states, behaving in ways that don't occur anywhere in our solar system. 55 Cancri E and planets like it are natural laboratories for studying physics under conditions we can't recreate on Earth. Now let's address a question you might be wondering. If there's all this diamond inside 55 Cancri E, Is any of it on the surface? Could you, hypothetically, land on the planet and scoop up diamond from the ground? The answer is almost certainly no. Here's why. Remember, 55 Cancri E orbits extremely close to its star. The surface temperature on the day side is around 2,400 degrees Celsius. At that temperature, most rocks melt. Even diamond, despite being incredibly heat resistant, would be approaching its stability limit. Diamond is stable at high pressures and moderate temperatures. But at very high temperatures and low pressures, like on the surface of a planet, diamond can revert to graphite. The transformation is slow at room temperature, which is why diamonds last forever in jewelry. But at 2400 degrees Celsius, the transformation would be much faster. Any diamond that somehow made it to the surface would likely convert to graphite, or even sublimate into carbon vapor. The precious crystalline structure would be lost. The diamond exists deep underground, protected by layers of rock and metal, held in its crystalline form by the immense pressure. It's locked away, forever beyond reach, forever hidden from view. And that's actually fitting in a poetic way. The most valuable substance humans have ever coveted, existing in quantities beyond comprehension, but eternally inaccessible. A cosmic treasure vault with no key. But let's imagine, just for a moment, that we could somehow reach 55 Cancri A, that we had spacecraft capable of traveling 40 light years and surviving the hellish environment, that we could drill through the molten surface and into the mantle below. What would we find? Picture descending through layers of rock and metal, the temperature rising, the pressure increasing. Kilometers down, tens of kilometers, hundreds, the rock around you transitions from familiar silicates to more exotic minerals, stable only under pressure. And then you reach it, the diamond layer. Your drilling equipment touches crystalline carbon, and suddenly you're surrounded by it. Not gemstones, not jewelry quality crystals, but massive, solid diamond. Walls of it extending in all directions. It wouldn't sparkle like diamonds in a jeweler's window. There's no light down here, no air for your eyes to see. It would be dark, hot, crushed under unimaginable weight. The diamond would be opaque, filled with impurities and inclusions from the planet's formation. But it would be diamond nonetheless, trillions of tons of it, forming a layer that could be hundreds or thousands of kilometers thick. Running your hand along the wall, if you could somehow survive the heat and pressure, you'd be touching the hardest substance in nature. You'd be standing in the universe's ultimate treasure chamber, surrounded by more wealth than all of human civilization has ever created. And then reality returns. We can't go there. We can't mine it. We can't even see it directly. It exists, vast and real, but forever beyond our grasp. Which brings us to an interesting philosophical question. Does the diamond have value if we can never access it? Does its existence mean anything if it can never be used, never be held, never be traded? I'd argue yes, because the value of 55 Cancri E isn't economic. It's scientific and philosophical. This planet tells us something profound about the universe we live in. It tells us that nature can create wonders far exceeding anything humans can build. It reminds us that the periodic table of elements, those 118 simple building blocks, can combine in an almost infinite variety of ways to create structures we never imagined. It demonstrates that the universe is not just a cold, empty void, but a place of staggering creativity, where matter itself is sculpted by forces into forms both strange and beautiful. And perhaps most importantly, it humbles us. It reminds us that for all our technology, all our knowledge, all our achievements, there are still places we cannot go, things we cannot touch, mysteries we may never fully solve. The diamond planet stands as a monument to the vast unknown that still lies before us. A challenge, an invitation, a reminder that we've barely begun to explore the wonders of the cosmos. Now let's take a detour into a fascinating what-if scenario. One that will help us understand just how unique and strange carbon planets really are. Let's imagine two planets born at the same time from the same protoplanetary disk, with the same mass and size. The only difference, one forms in an oxygen-rich region, the other in a carbon-rich region. Call them Planet O and Planet C. Planet O forms the way Earth did. The protoplanetary disk in its region has more oxygen than carbon, so most of the carbon bonds with oxygen to form gases, carbon monoxide and carbon dioxide. These gases either escape into space or end up in the planet's atmosphere. The remaining oxygen bonds with silicon, forming silicates, the minerals that make up most of Earth's crust and mantle. These include minerals like olivine, pyroxene, feldspar. They're stable, they're abundant, and they form the basic building blocks of rocky planets in our solar system. Planet O also has iron and nickel that sink to the center during formation, creating a metallic core. As the planet grows and its interior heats up, the rock becomes partially molten, allowing heavier elements to sink and lighter elements to rise. This process, called differentiation, creates distinct layers, a dense iron core, a thick rocky mantle, and a thinner crust on the surface. When Planet O's interior is hot enough, convection begins in the mantle. Hot rock slowly rises, cools, and sinks back down in a continuous cycle. This convection drives plate tectonics on the surface, continents drifting, mountains rising, oceanic crust being recycled. The iron core, hot and liquid, generates a magnetic field through the dynamo effect. This field extends far into space, creating a magnetosphere that shields the planet from harmful radiation. If Planet O is the right distance from its star, not too hot, not too cold, and if it has an atmosphere with greenhouse gases like carbon dioxide and water vapor, it could have liquid water on its surface. And liquid water, as we know, is the foundation for life as we understand it. Planet O would be a world familiar to us. Rocky continents, vast oceans, an atmosphere of nitrogen and oxygen, clouds drifting across blue skies. It would look like Earth, feel like Earth, be like Earth. Now let's look at Planet C. Planet C forms in a carbon-rich region. Here there's more carbon than oxygen. The oxygen bonds with carbon, forming carbon monoxide and dioxide, but there's carbon left over, lots of it. This excess carbon bonds with other elements. It forms silicon carbide instead of silicates. It forms iron carbides instead of pure iron. It forms a whole suite of carbon-bearing minerals that are rare or non-existent on Planet O. As Planet C grows, it incorporates massive amounts of carbon compounds. When it undergoes differentiation, the result is very different from Planet O. The core might be iron carbide rather than pure iron. Iron carbide is harder and denser than pure iron, with different melting points and electrical properties. It might not generate a magnetic field as efficiently, or it might generate a different kind of field. The mantle isn't made of silicate rocks, it's made of silicon carbide and other carbon compounds. Silicon carbide is incredibly hard, second only to diamond. It's also less prone to melting and convection than silicates. This means Planet C's interior might be more rigid. Plate tectonics, if they occur at all, would be sluggish. The surface might be a stagnant lid, not recycling material the way Earth's surface does. And deep in the mantle, where pressure is extreme, all that excess carbon crystallizes into diamond. Layers of it compressed into solid form by the weight above. On the surface, Planet C would look alien. If it's the right temperature, there might be lakes or oceans, but not of water. With so little oxygen available, water is scarce. Instead, the oceans might be liquid hydrocarbons, similar to the methane and ethane lakes on Saturn's moon Titan. The atmosphere could be rich in carbon monoxide, carbon dioxide, methane, and other carbon compounds. The sky might have a brownish or orange tint from organic hazes. The rocks wouldn't be grey or brown granite and basalt. They'd be darker, made of silicon carbide and graphite. Mountains would be harder, more resistant to erosion. Volcanoes, if they exist, might erupt not silicate lava, but molten carbides or even liquid carbon under certain conditions. And if you could drill deep enough, past the carbide crust, through the rigid mantle, you'd reach the diamond layers, the planet's hidden wealth, locked away in the depths. Planet C would be, in almost every way, a different kind of world, built from the same basic elements, but with a different ratio, creating an entirely different outcome. Now here's the thing, both planets are possible. Both could form under the right conditions. Neither violates any laws of physics. The difference is just chemistry. the relative abundances of elements and how they bond. But the implications of that difference are staggering. Because chemistry determines geology, and geology determines whether a planet can support life. On planet O, with its active plate tectonics and magnetic field, the surface is dynamic. Continents move, volcanoes bring nutrients from the interior, water circulates through the crust. These processes create and maintain the conditions necessary for life. Earth's plate tectonics, for instance, play a crucial role in regulating the planet's climate. Carbon dioxide released by volcanoes is absorbed by weathering of rocks and eventually deposited on the ocean floor as carbonate minerals. This carbon is then recycled back into the mantle at subduction zones to be released again by future volcanoes. This carbon cycle keeps Earth's atmosphere stable over millions of years. Too much CO2 and the planet heats up, accelerating weathering and removing CO2. Too little, and volcanic outgassing adds more. It's a natural thermostat. Planet C, with its rigid, stagnant lid, might not have this cycle. Without active plate tectonics, carbon dioxide might not be efficiently recycled. The atmosphere could become locked in one state, either too thick, creating a runaway greenhouse, or too thin, leaving the planet frozen. And without a strong magnetic field, if the iron carbide core doesn't generate one efficiently, Planet C would be constantly bathed in stellar radiation and solar wind. Any atmosphere might slowly erode away, blown into space by charged particles from the star. Does this mean Planet C is lifeless? Not necessarily. Life is resourceful, and we've learned never to underestimate its ability to adapt to extreme conditions. But it does mean that if life exists on a carbon planet, it would be fundamentally different from life on Earth. Earth life is based on carbon chemistry, but it relies on water as a solvent. Our cells, our biochemistry, everything that makes us alive happens in liquid water. Carbon forms the structural framework, but water is the medium. On a carbon planet, if there's little water, life would need a different solvent. Could hydrocarbons serve that role? On Titan, Saturn's largest moon, there are lakes and seas of liquid methane and ethane. Some scientists have speculated about exotic forms of life that could use these hydrocarbons instead of water. Such life would have completely different biochemistry. Its cells would be structured differently. Its metabolism would run on different chemical reactions, and it would likely operate at much lower temperatures than Earth life. Or perhaps on a carbon planet, life could be based on silicon instead of carbon. Silicon is directly below carbon on the periodic table, meaning it has similar bonding properties. Silicon-based life is a staple of science fiction. And while there are good chemical reasons why carbon is superior for biology, in an environment rich in silicon carbide, who knows? These are wild speculations, of course. We have exactly one example of life in the universe, Earth life, and it's all based on the same fundamental chemistry. We have no idea if other forms of life are possible, but the existence of carbon planets like 55 Cancri E forces us to confront these questions. Because if such worlds are common, and if even a tiny fraction of them have conditions suitable for some kind of life, the galaxy could be populated by organisms more alien than anything we've imagined. And that brings us back to a central theme of this exploration: diversity. Our solar system gave us a limited sample size. We have rocky planets, gas giants, icy moons, and not much else. For centuries, astronomers assumed other planetary systems would be similar. We expected to find solar system analogues, systems with small rocky worlds close in, giant planets farther out, everything arranged in neat, orderly orbits. The reality has been far stranger. We've found hot Jupiters where gas giants shouldn't be able to form. We've found super-Earths, a category of planet completely absent from our solar system. We've found planets orbiting binary stars, planets orbiting dead stars, planets with orbits so eccentric they look like comets. And we found hints of carbon planets, worlds where the very rocks beneath the surface are fundamentally different from anything in our solar system. This diversity is a gift to science. Each new type of planet is a natural experiment, a test case for our theories of planetary formation and evolution. Each one teaches us something new about how matter behaves under different conditions. 55 Cancri, whether it's truly a diamond planet or something else, is a window into a class of worlds we never anticipated. It's a reminder that the universe's creativity far exceeds our own. And it raises a profound question. If planets can be this different in composition, how different might the life that evolves on them be? We don't have an answer. Not yet, but we're starting to ask the right questions. And sometimes, in science, that's the most important step. So far, we've talked about diamond planets forming in the protoplanetary disks around young stars. But there's another pathway to creating diamond worlds, one even more dramatic and final. One that involves the death of stars themselves. Let me tell you about white dwarfs. When a star like our Sun exhausts its nuclear fuel, it doesn't go out with a bang. It goes out with a whimper. The fusion reactions in its core gradually cease, and without the outward pressure from fusion to balance gravity, the core begins to contract. As it contracts, it heats up, igniting fusion in the layers surrounding the core. This causes the star's outer envelope to expand dramatically. The star becomes a red giant, swelling to hundreds of times its original size. When the Sun becomes a red giant in about 5 billion years, it will expand beyond Earth's current orbit. But this phase doesn't last. Eventually, the outer layers are expelled into space, forming a beautiful planetary nebula. And what's left behind is the core, a dense, hot remnant about the size of Earth, but with a mass roughly equal to the Sun. This remnant is a white dwarf. White dwarfs are bizarre objects. They're no longer producing energy through fusion. They're simply cooling down, radiating away their residual heat over billions of years. But despite having a mass similar to the Sun, they're compressed into a volume similar to Earth. The compression creates extraordinary densities. A teaspoon of white dwarf material would weigh about 5 tons. The pressure and density are so extreme that matter exists in a degenerate state where quantum mechanical effects prevent further collapse. Most white dwarfs are composed primarily of carbon and oxygen. These elements are the ash left over from helium fusion in the star's core. As the white dwarf cools over billions of years, something remarkable happens. The carbon and oxygen begin to crystallize. Just like water freezing into ice, the carbon in a white dwarf can solidify as it cools. And because of the immense pressure, the carbon doesn't become graphite. It becomes diamond. This isn't speculation. In 2004, astronomers discovered a white dwarf designated BPM 37093, nicknamed Lucy after the Beatles song Lucy in the Sky with Diamonds. Observations of this white dwarf's pulsations, tiny oscillations in its brightness, allowed scientists to probe its interior structure. The data suggested that up to 90% of Lucy's mass has crystallized into diamond. That's a 10 billion trillion carat diamond, a 1 followed by 34 zeros. Lucy is essentially a diamond the size of Earth, and Lucy isn't unique. Every white dwarf composed primarily of carbon will eventually crystallize as it cools. The galaxy is filled with these stellar diamonds, ancient relics of stars that died billions of years ago, now frozen into crystalline form. But white dwarfs, despite being made of diamond, aren't planets. They're stellar remnants, held up against collapse not by chemical bonds or structural strength, but by quantum degeneracy pressure. However, white dwarfs can have planets, and those planets can become diamond worlds through a different process. Imagine a planet orbiting a sun-like star. For billions of years, it enjoys stable conditions, perhaps even developing life. But then the star ages. It swells into a red giant, and the planet finds itself engulfed in the star's outer atmosphere. If the planet is small and dense enough, it can survive this. It plunges through the star's tenuous outer layers, suffering extreme heating and atmospheric stripping, but its solid core endures. When the star finally ejects its outer envelope and becomes a white dwarf, the planet emerges, scarred but intact. Now the planet orbits a white dwarf, a dense, hot remnant that bathes the planet in intense radiation. Any remaining atmosphere is blasted away. The surface is heated to thousands of degrees, but deep in the interior, protected by layers of rock and metal, carbon compounds are subjected to extreme pressure. If the planet had significant carbon content, perhaps from its formation, or perhaps from material accreted during its passage through the star's outer layers, that carbon crystallizes. The result is a planet with a diamond interior, orbiting a diamond star, a cosmic jewel box on a scale beyond imagination. We've actually discovered planets orbiting white dwarfs. In 2020, astronomers found the first intact planet around a white dwarf, designated WD 1856b. It's a giant planet, about the size of Jupiter, orbiting its white dwarf every 34 hours. The planet's survival is remarkable. It must have either formed far from the star and migrated inward after the star became a white dwarf, or it somehow survived the red giant phase. Either way, its existence proves that planets can persist through their star's death. Could WD 1856b have a diamond core? Possibly. If it formed with carbon-rich materials, its core might contain significant diamond. We don't have enough data to say for certain, but it's a tantalizing possibility. And there's an even more exotic scenario, planets forming from the debris of stellar death itself. When a star becomes a white dwarf, it ejects its outer layers into space. This material forms a planetary nebula, a glowing shell of gas expanding outward at thousands of kilometers per second. Over tens of thousands of years, the nebula dissipates, its material mixing with the interstellar medium. But sometimes the ejected material doesn't disperse immediately. If the white dwarf has a companion star, the ejected material can be captured into orbit around the binary system. Over time, this material can cool, condense, and potentially form new planets. These second-generation planets would be strange worlds indeed, formed not from the primordial disk of a young star, but from the processed ashes of a star's death, enriched in carbon and oxygen from helium fusion. Such planets could be extremely carbon-rich, potentially with diamond layers exceeding anything in first-generation planets like 55 Cancri e. We haven't confirmed any such planets yet, but astronomers are actively searching. The discovery of a second-generation planet around a white dwarf would be a major finding, opening up entirely new questions about planetary formation and evolution. Now let's talk about the ultimate diamond worlds, the ones orbiting neutron stars and pulsars. Remember PSR JWST 19-1438b, the planet I mentioned earlier? It's orbiting a millisecond pulsar, and is thought to be almost entirely diamond, with a mass similar to Jupiter. The leading theory for this planet's origin is even more dramatic than anything we've discussed so far. It's thought to be the remnant of a star. Here's the scenario. Two stars form a binary system. One is more massive than the other. The massive star evolves faster, eventually exploding as a supernova and leaving behind a neutron star, a collapsed core even denser than a white dwarf, with a mass about 1.4 times the Sun compressed into a sphere just 20 kilometers across. The companion star continues to evolve. Eventually it swells into a red giant, but now instead of simply expanding and ejecting its outer layers into space, those layers are pulled toward the neutron star by intense gravity. The neutron star begins accreting material from its companion. This material forms an accretion disk, spiraling inward and eventually crashing onto the neutron star's surface. The energy released in this process spins up the neutron star, causing it to rotate faster and faster. Over millions of years, the neutron star strips away most of the companion star's mass, leaving only the core. That core, composed primarily of carbon and oxygen, is subjected to extreme tidal forces and radiation from the pulsar. It's compressed, crystallized, and transformed into a planet-sized diamond. The end result is PSR JWST 719-1438b, a diamond world orbiting a dead star, the remnant of a cosmic catastrophe. It's a memorial to a star that once shone, now reduced to a crystallized core in eternal orbit. And it might not be alone. Other millisecond pulsars might have similar companions. As our ability to detect small objects around pulsars improves, we might discover more of these diamond remnants. Each one would tell a story of stellar evolution, of binary interactions, of matter subjected to conditions so extreme that it transforms into something entirely new. These diamond worlds, whether around white dwarfs, pulsars, or main sequence stars, all share something profound. They're reminders of how matter recycles through the universe. The carbon in a diamond planet wasn't always carbon. It was once hydrogen in the early universe. That hydrogen was pulled together by gravity, forming a star. Inside that star, fusion transformed hydrogen into helium, and helium into carbon. When the star died, it scattered that carbon into space. The carbon became part of a gas cloud, which collapsed to form a new star and planets. In those planets, under pressure, the carbon became diamond. Billions of years from now, those planets might be consumed by their stars, or ejected into interstellar space, or disrupted by gravitational interactions. The diamond will be broken apart, its carbon atoms freed to begin the cycle again. Nothing in the universe is permanent. Even diamond, the hardest substance we know, is just a temporary arrangement of atoms. Given enough time, even it will transform into something else. But for now, for this brief moment in cosmic history, these diamond planets exist. They glitter in the darkness, monuments to the universe's ability to create beauty and wonder from the simplest building blocks. And we, briefly alive on our own small world, get to discover them. We get to use our minds and our tools to reach across the light years and understand something about these distant, impossible places. It's a privilege and a reminder that the universe is not just something to be observed, but something to be celebrated. Let's talk about how we actually study these distant worlds. Because understanding 55 Cancri E and other exoplanets requires some of the most sophisticated technology humans have ever built. When you look up at the night sky, you see stars, thousands of them, twinkling in the darkness. But you don't see any planets around those stars, even though we now know most stars have planets. This isn't because we're not looking hard enough. It's because planets are incredibly difficult to observe. Consider the challenge. A typical exoplanet reflects or emits maybe 1 billion times less light than its host star. That's like trying to spot a firefly next to a stadium floodlight from 1,000 miles away. The star's light completely overwhelms the faint signal from the planet. And distance makes everything worse. 55 Cancri E is 40 light years away. That means light from the planet takes 40 years to reach us. The photons hitting our telescopes today left the planet in 1985. At that distance, even the star appears as just a point of light. The planet, much smaller and fainter, is completely lost in the star's glare. So how do we detect exoplanets at all? The breakthrough came from using indirect methods. Techniques that detect a planet's influence on its star, rather than seeing the planet directly. The radial velocity method, which I mentioned earlier, measures the tiny wobble a planet creates in its star's motion. When a planet orbits, it doesn't orbit around the star. Both planet and star orbit around their mutual center of mass. For a star with a planet, this creates a wobble. Sometimes the star moves toward us, sometimes away. This motion changes the wavelength of the star's light through the Doppler effect. Light from the star is slightly blue shifted when it's moving toward us, slightly red shifted when moving away. Modern spectrographs can measure these wavelength shifts with incredible precision, down to changes of a few meters per second, about the speed of a person walking. This method is how we measured 55 Cancri E's mass. By watching how much the star wobbles, we can calculate how much gravitational pull the planet exerts, which tells us the planet's mass. But radial velocity doesn't tell us the planet's size. For that, we need the transit method. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. The star appears to dim slightly, usually by less than 1%, for a few hours while the planet transits. By measuring how much the star dims, we can calculate the planet's radius. A bigger planet blocks more light, causing a deeper transit. The duration of the transit tells us about the planet's orbit. NASA's Kepler Space Telescope revolutionized exoplanet science using this method. Launched in 2009, Kepler stared at a single patch of sky containing about 150,000 stars, continuously monitoring their brightness for 4 years. The data Kepler collected is astonishing. Imagine taking a photograph of the same stars every 30 minutes for 4 years straight, measuring the brightness of each star with enough precision to detect a transit. The patience and precision required is almost unimaginable. But it worked. Kepler discovered over 2,600 confirmed exoplanets and identified thousands more candidates awaiting confirmation. It taught us that planets are common, most stars have them, and that planetary systems come in extraordinary variety. 55 Cancri-E's transit was first observed in 2011, though the planet had been detected by radial velocity in 2004. The transit observations gave us the planet's radius, and combined with the mass from radial velocity measurements, we calculated its density. That density, higher than any planet in our solar system, is what sparked the diamond planet hypothesis. But these methods only give us basic information: mass, radius, orbital period. To really understand what a planet is made of, we need to study its atmosphere, and that requires spectroscopy. Spectroscopy is the analysis of light broken into its component wavelengths, essentially creating a rainbow and studying it in detail. Different atoms and molecules absorb and emit light at specific wavelengths, creating a unique fingerprint. When a planet transits its star, some of the star's light passes through the planet's atmosphere. Gases in that atmosphere absorb specific wavelengths, leaving dark lines in the spectrum. By identifying which wavelengths are absorbed, we can determine what gases are present. This is called transmission spectroscopy, and it's one of the most powerful tools we have for studying exoplanet atmospheres. In 2016, astronomers used the Hubble Space Telescope to perform transmission spectroscopy on 55 Cancri-E. They detected hydrogen and helium, as expected, but also found evidence of hydrogen cyanide, a carbon-nitrogen compound. This was significant because hydrogen cyanide contains carbon, supporting the idea that the planet is carbon-rich. The presence of this particular molecule tells us something about the chemistry occurring in the planet's atmosphere. But transmission spectroscopy has limitations. It only works during transits, and it only probes the atmosphere. It can't tell us anything directly about the planet's interior. To go deeper, we need other techniques. One promising method is thermal emission spectroscopy. All objects emit infrared radiation based on their temperature. Hot objects emit more and at shorter wavelengths. By measuring a planet's infrared emission, we can estimate its temperature and potentially identify specific molecules in the atmosphere that emit at characteristic wavelengths. 55 Cancri-E is hot enough that it emits significant infrared radiation. Observations with the Spitzer Space Telescope measured the planet's dayside temperature at around 2,400 degrees Celsius. But interestingly, they also detected temperature variations, suggesting that heat isn't evenly distributed across the surface. These temperature maps give us clues about the planet's atmosphere and interior structure. If heat is transported efficiently from the day side to the night side, it suggests a thick atmosphere or vigorous winds. If the day side is much hotter than the night side, it suggests the atmosphere is thin or the planet is tidally locked with little heat transport. For 55 Cancri-E, the data suggests complex atmospheric dynamics that we're still working to understand. But all these methods, radial velocity, transits, spectroscopy, are reaching their limits. To truly understand exoplanets, especially small rocky ones like 55 Cancri-E, we need better technology. Enter the James Webb Space Telescope. Launched in December 2021, JWST is the most powerful space telescope ever built. It's designed primarily for infrared observations, which is perfect for studying exoplanets. Infrared light is essentially heat radiation. Planets emit infrared light based on their temperature. And because stars emit less infrared light than visible light, planets are easier to detect in the infrared. The contrast between planet and star is less extreme. JWST's mirrors are coated with gold, which reflects infrared light efficiently. Its instruments are cooled to near absolute zero to minimize thermal noise. And it's positioned at a location in space called the L2 Lagrange point, where it's shielded from the Sun, Earth, and Moon, allowing it to observe the faint infrared glow of distant planets without interference. Early observations from JWST have already revolutionized our understanding of exoplanet atmospheres. It's detected water vapor, carbon dioxide, methane, and other molecules in the atmospheres of several exoplanets. It's measured temperature profiles with unprecedented precision. And it's on the list to observe 55 Cancri e. When JWST turns its gaze toward this diamond planet, it will collect data far more detailed than anything we have. It might detect new molecules in the atmosphere. It might measure variations in temperature and composition across the planet's surface. It might even find evidence of volcanic activity or other dynamic processes. Every new observation has the potential to confirm, refine, or completely overturn our understanding of what this planet is. But even JWST has limitations. It's an infrared telescope, not an imager. It can study a planet's light spectrum, but it can't take a photograph of the planet's surface. For that, we need direct imaging. Direct imaging is the holy grail of exoplanet observation. It means actually capturing photons from the planet itself, creating an image that shows the planet as a distinct object separate from its star. This is incredibly difficult. Remember, the planet is about 1 billion times fainter than its star. It's like trying to photograph a candle next to a lighthouse. To achieve direct imaging, astronomers use special techniques to block the star's light. One method uses a coronagraph, a device that creates an artificial eclipse, blocking the star and allowing the faint light from nearby planets to be seen. Another method uses star shades, giant specialized shaped screens flown in space between the telescope and the star. The star shade blocks the star's light before it reaches the telescope, allowing planets to be imaged. These techniques have successfully imaged a few exoplanets, mostly young hot gas giants that orbit far from their stars and emit significant infrared light. But imaging small rocky planets like 55 Cancri, which orbit close to their stars, remains beyond our current capabilities. Future missions aim to change that. NASA is studying concepts for a space telescope with a star shade, specifically designed to directly image Earth-like exoplanets. The European Space Agency is developing similar concepts. If such a mission is built and launched, probably in the 2030s or 2040s, it could potentially image 55 Cancri. Not in detail, perhaps just a few pixels, but we'd see it as an actual object, not just a measurement. Imagine that moment, the first photograph of a diamond planet. A tiny point of light, perhaps showing brightness variations as the planet rotates, hinting at surface features. Cloud patterns, if the atmosphere is complex, temperature variations between day and night sides. It would be historic. A new window into a world we've only been able to imagine. But until that day comes, we rely on the indirect methods, the careful measurements, the detailed spectra, the mathematical models. We build our understanding piece by piece, observation by observation. And with each new piece of data, the picture becomes clearer. 55 Cancri is slowly revealing its secrets. Not all at once, not easily, but gradually, patiently, as science always works. The diamond planet remains mysterious, but we're getting closer to understanding it. And the journey of discovery is, in many ways, as valuable as the destination. Now we arrive at perhaps the most profound question of all. Could a diamond planet host life? At first glance, the answer seems obviously no. 55. Cancri's surface is hot enough to melt rock. It has no liquid water. Its atmosphere is vaporized stone. It's tidally locked, with one side eternally baking under the star's glare and the other plunged into darkness. It's subjected to intense stellar radiation and flares. These conditions would be instantly lethal to any Earth life. Even the most extreme extremophiles, organisms that thrive in Earth's harshest environments, couldn't survive. But let's think more carefully. Because life is surprising and the universe has a way of defying our expectations. First, let's clarify what we mean by life. This is actually a surprisingly difficult question. There's no universally agreed upon definition of life, but most scientists agree on a few key characteristics. Life is organized. It has structure, whether that's a cell membrane separating inside from outside, or more complex arrangements of tissues and organs. Life uses energy. It takes in resources from its environment, sunlight, chemical compounds, heat, and uses that energy to maintain itself and grow. Life reproduces. It makes copies of itself, passing information to the next generation. Life evolves. Over many generations, populations of living things change in response to their environment, becoming better adapted. By these criteria, viruses are borderline. They reproduce but don't metabolize on their own. Fire metabolizes and grows but doesn't evolve in a Darwinian sense. Only living things check all the boxes. Now, all the life we know, every organism on Earth shares a common ancestry and uses the same basic chemistry. DNA stores genetic information. Proteins do most of the work. Cells are enclosed by lipid membranes. Metabolism uses specific chemical reactions, many involving phosphates and ATP. But is this the only way life can work? Or is Earth life just one example among many possible forms? This question has captivated scientists for decades. The search for extraterrestrial life has traditionally focused on finding places similar to Earth. Planets with liquid water, moderate temperatures, protective atmospheres. The logic is sound. We know these conditions can support life because they support life here. But increasingly, scientists are considering more exotic possibilities. What if life can arise under conditions completely different from Earth? One place to look is right here in our solar system. Saturn's moon Titan has lakes and seas of liquid methane and ethane with temperatures around 180 degrees Celsius. Some scientists have proposed that life could potentially use these liquid hydrocarbons as a solvent instead of water. Such life would be bizarrely alien. Its biochemistry would be completely different, operating at temperatures where water is solid ice and where chemical reactions occur much more slowly. But thermodynamically, it's not impossible. Another possibility is subsurface oceans on icy moons. Jupiter's moon, Europa, and Saturn's moon, Enceladus, both have global oceans beneath their icy crusts, kept liquid by tidal heating. These oceans are dark, cold, and isolated from sunlight, but they're in contact with rocky cores below, potentially providing chemical energy. We know life on Earth can survive without sunlight. Deep-sea hydrothermal vents host thriving ecosystems powered by chemical energy. Could similar ecosystems exist in Europa's ocean? These examples push the boundaries of where we think life might exist, but they're still water-based, still using familiar chemistry, just in unfamiliar environments. What about truly alien life? Life based on different chemistry entirely? One frequently discussed alternative is silicon-based life. Silicon is directly below carbon on the periodic table, meaning it has similar bonding properties. It can form chains and complex molecules, just like carbon. But there are problems. Silicon-oxygen bonds are very stable, meaning silicon tends to form silicon dioxide, quartz, rather than the diverse compounds carbon creates. Silicon compounds are generally less flexible, less soluble in water, and less capable of the complex chemistry life requires. Still, in an environment rich in silicon and poor in carbon, like perhaps the surface of a carbon-depleted silicate planet, could silicon biochemistry emerge? We don't know. It remains theoretical speculation. Now let's bring this back to carbon planets and 55 Cancri e. On the surface of 55 Cancri e, life seems impossible. The temperature alone rules out any chemistry we associate with life. Proteins denature, DNA breaks down, cell membranes would vaporize. But what about in the planet's interior? Deep underground, beneath the scorching surface, the temperature drops. There might be a zone, perhaps tens or hundreds of kilometers down, where temperatures are moderate, say 0 to 100 degrees Celsius. At those depths, if there are pockets or layers of liquid, perhaps molten carbides, or aqueous fluids released from minerals under pressure, you have the basic ingredients for chemistry. And in a carbon-rich environment, you have abundant carbon compounds, organic molecules, hydrocarbons, perhaps even complex carbon structures formed under pressure. Could life emerge in such an environment? Life that exists in cracks and pores in the rock, feeding on chemical gradients, powered by the heat flowing from the planet's interior? It's wildly speculative. We have no evidence for it, but we also can't rule it out entirely. Earth has a deep biosphere. Microorganisms living in rock pores kilometers below the surface, deriving energy from chemical reactions with the minerals around them. These organisms can survive at high temperatures, high pressures, with no light and minimal nutrients. If Earth's deep biosphere can thrive, why not a deep biosphere on 55 Cancri? The challenges are immense, of course. The planet's interior pressure is far higher than Earth's. The chemistry is different. There might not be liquid water. Tidal stresses from the planet's close orbit could generate heat, but also create instability. But life, as we've learned again and again, is remarkably tenacious. It finds a way to exploit any available niche, any source of energy, any stable environment. And here's an intriguing thought. If life did exist in 55 Cancri-E's interior, it would be living in a diamond matrix, surrounded by crystalline carbon, existing in microscopic pores between diamond grains. Life encased in diamond. It's a poetic image, and while almost certainly wrong, it illustrates how much we still have to learn about the possibilities for life in the universe. But let's consider an even more radical idea. What if the diamond itself is relevant to life? This might sound absurd. Diamond is just a mineral, an inert crystal. It doesn't live, it doesn't metabolize or reproduce. But think about the role minerals play in the origin of life on Earth. One leading theory for how life began involves clay minerals. Clays have layered structures with charged surfaces. Organic molecules can stick to these surfaces, becoming concentrated. The clay structure can even template certain chemical reactions, helping organic molecules organize themselves. Some scientists think life might have first emerged on clay mineral surfaces, using the clay as a scaffold to build the first self-replicating molecules. Could diamond play a similar role? Diamond surfaces are highly structured and can be chemically modified to attach different molecules. In nanotechnology, scientists use diamond surfaces as substrates for growing organic structures. In a carbon-rich environment with diamond surfaces exposed to organic-rich fluids, could the diamond act as a catalyst or template for prebiotic chemistry? It's a stretch. Diamond is chemically inert compared to clays, but under the extreme conditions in a super-Earth's interior, high temperature, high pressure, unusual chemistry, who knows what reactions might be possible. I want to be clear, there is no evidence for life on 55 Cancri-E. None. This is speculation piled on speculation, thought experiments to stretch our minds and consider possibilities we might otherwise dismiss. The likelihood of life on 55 Cancri-E is, in my estimation, extremely low. The conditions are too extreme, the environment too hostile, the chemistry too uncertain. But the broader question, can carbon planets in general host life, is more open. Not all carbon planets are like 55 Cancri-E. Some might orbit at greater distances, where temperatures are moderate. Some might have thick atmospheres that distribute heat and moderate temperature extremes. Some might have retained water despite being carbon-rich. A carbon planet in a star's habitable zone, the region where liquid water can exist on the surface, would be an extraordinarily interesting target for the search for life. Such a planet would have different geology, different chemistry, different atmospheric composition, but it might just possibly have conditions where some form of life could emerge. And if it did, that life would be adapted to a carbon-rich world. It might use different metabolic pathways, different structural molecules, different strategies for survival. Studying such life, if we ever find it, would revolutionize biology. It would give us a second example of life's chemistry, allowing us to distinguish between what's universal about life and what's specific to Earth. It would answer one of the deepest questions in science. Is life a cosmic inevitability emerging wherever conditions allow? Or is it a rare accident, a contingent outcome of unlikely events? We don't know, but worlds like 55 Cancri, strange and extreme as they are part of how we'll find out. Because the search for life isn't just about finding places exactly like Earth, it's about exploring the full range of environments where life might exist. It's about challenging our assumptions and broadening our definitions. And it's about recognizing that the universe is full of surprises, places we never imagined, with conditions we never anticipated, where nature might have found solutions we never considered, The diamond planet, hostile as it is, reminds us of this. It reminds us to keep looking, keep questioning, keep wondering, because somewhere out there, among the billions of worlds, life might be thriving in a place we'd never think to look. And the only way we'll find it is by exploring everywhere we can, with open minds and boundless curiosity. Let's take a step back from the science for a moment and consider something more philosophical. What does the diamond planet mean? Not scientifically, but culturally, psychologically, existentially. For most of human history, diamonds have been among the most valued objects on Earth. They're rare, beautiful, incredibly durable. They've symbolized wealth, power, eternal love. Wars have been fought over them. Empires have risen and fallen based on controlling diamond mines. The value of diamonds is partly practical. They're useful for cutting and drilling due to their hardness, but mostly their value is symbolic. We value them because they're rare and because we've collectively agreed they're valuable. But 55 Cancri E contains more diamond than all the mines on Earth combined, multiplied by trillions. If we could somehow access it, diamonds would become worthless overnight. They'd be as common as gravel. This creates an interesting paradox. The most valuable substance we know exists in such quantities that it has no value. Or does it? Perhaps the diamond planet is valuable precisely because we can't reach it. Its value isn't economic. It's inspirational. It represents something beyond acquisition, beyond ownership. It's a reminder that the universe contains wonders that exist for their own sake, not for our use. There's something almost zen about this. The ultimate treasure, eternally out of reach. It challenges our consumer mindset, our tendency to value things based on whether we can possess them. And it raises interesting questions about value itself. What makes something valuable? Scarcity, utility, beauty, cultural meaning. On Earth, a single diamond can be valuable, but a planet made of diamond has a different kind of value. The value of wonder, the value of expanding our understanding, the value of knowing such a thing exists. This is the value of the impossible made possible. For centuries, planets beyond our solar system were impossible. We knew they probably existed. Why would only our sun have planets, but we had no way to detect them? They were beyond our technological reach, beyond observation, existing only in speculation. Then, in 1995, we found the first one. And the impossible became possible. The realm of speculation became the realm of science. Each new class of exoplanet we discover expands our sense of what's possible. Hot Jupiters taught us that gas giants can migrate inward. Super Earths taught us that rocky planets can be much larger than Earth. Water worlds taught us that planets can be dominated by oceans. And carbon planets, diamond worlds like 55 Cancri E, teach us that planetary chemistry can be fundamentally different from what we see in our solar system. Each discovery is valuable not for what it gives us materially, but for how it changes our thinking. It breaks assumptions. It forces us to reimagine what we thought we understood. This is the engine of scientific progress. We build models of how we think the universe works. Then we make observations that don't fit those models. So we revise the models, making them more accurate, more comprehensive, better able to explain reality. The diamond planet didn't fit our models. We didn't predict its existence. And that's precisely why it's so valuable scientifically. But there's another kind of value here, one that's harder to quantify, the value of inspiration. Think about the person reading this right now, or rather listening to this video. Maybe you're a student wondering what to study. Maybe you're considering a career in science. Maybe you're just someone who finds space fascinating. The diamond planet's existence might inspire you. It might make you realize that the universe is stranger and more wonderful than you imagined. It might spark a curiosity that leads you to study astronomy, planetary science, chemistry, physics, and maybe years from now you'll be the one who makes the next great discovery. Maybe you'll find an even stranger planet, or figure out how carbon planets form, or develop the technology to image distant worlds directly. This is how progress happens, not through single individuals working alone, but through chains of inspiration and discovery, each person building on what came before, each new finding inspiring the next generation to push further. The diamond planet is a link in that chain. It's part of humanity's ongoing journey to understand the universe we inhabit. And it serves another purpose. It humbles us. We live in an age of unprecedented technological capability. We've split the atom, sequenced the genome, connected billions of people through digital networks. We've landed robots on Mars and sent spacecraft beyond our solar system. It's easy to feel like we've mastered nature, like there are no limits to what we can achieve. The diamond planet reminds us otherwise. Here's something we know exists. We can measure it, study it, understand aspects of it, but we can't touch it. We can't reach it. We can't possess it. There are limits to our power. There are wonders that will forever remain beyond our grasp. And that's okay. It's even good. Because it means the universe will never run out of mysteries. There will always be something more to discover. Something else to inspire awe and curiosity. In a strange way, the inaccessibility of 55 Cancri air preserves its wonder. If we could mine it, it would become just another resource. But because we can't, it remains something more. A symbol of the vast, wild, incomprehensible universe that surrounds our tiny planet. Now, I want to address something. Some people, when they learn about exoplanets and the vast distances involved, feel despair. What's the point, they ask, of discovering worlds we can never visit? Why should we care about planets we'll never reach? I understand the sentiment, but I think it misses something crucial. We don't study distant planets because we want to visit them or exploit them. We study them because understanding the universe is intrinsically valuable. Knowledge for its own sake is worth pursuing. Every fact we learn about 55 Cancri E improves our understanding of planetary formation, chemistry, physics. That understanding helps us comprehend our own planet better. It provides context for Earth's place in the cosmos. And who knows? Maybe one day, distant descendants of humanity will develop technologies we can't imagine. Maybe they'll find ways to traverse interstellar distances. Maybe the planets we're discovering today will be destinations for explorers thousands or millions of years in the future. We're laying groundwork. We're cataloging the universe. We're creating a treasure map for future generations. But even if we never reach these distant worlds, even if humanity never develops faster than light travel or generation ships or whatever it would take, the knowledge is still valuable because we are the universe becoming aware of itself. We're made of atoms forged in stellar cores, arranged in patterns complex enough to contemplate our own existence. We're matter that can look outward and understand what we see. When we study a diamond planet 40 light years away, we're not separate observers looking at something alien. We're the universe examining a part of itself. We're one piece of the cosmos understanding another piece. That's profound. That's meaningful. That's valuable in a way that transcends practical utility. The diamond planet exists whether we observe it or not. But by observing it, by understanding it, we bring it into human consciousness. We make it part of our story, part of our intellectual heritage. Future generations will grow up knowing that planets can be made of diamond. They'll take it for granted, the way we take for granted that Earth is round or that atoms exist. What seems extraordinary to us will be ordinary to them, but it will still be true. 55 Cancri E will still be out there, orbiting its star, layers of crystalline carbon compressed in its interior. And humans will still look up at the night sky and wonder what else is out there, what other impossibilities are waiting to be discovered. Because that's what we do. We're a curious species. We explore, we question, we seek to understand. It's built into us, as fundamental as our DNA. The diamond planet is one answer to one question. But every answer generates new questions. How did it form? How many more are there? What else is possible? And so the journey continues. Each discovery is both an end and a beginning. We'll never run out of questions, never exhaust the mysteries of the universe. That's not a cause for despair, it's a cause for celebration. Because it means the adventure never ends. There will always be something new to discover, always another horizon to explore. Even if we never leave our own solar system, we can explore the universe through observation and understanding. We can map the cosmos, catalog its wonders, understand its rules. And that's a worthy endeavor. That's a noble pursuit. That's something worth dedicating our lives to. The diamond planet, impossible and real, valuable and worthless, distant and knowable, it represents all of this. It's a challenge and an invitation, a mystery and a revelation, and it's waiting for us to understand it. So where do we go from here? We've discovered a diamond planet, debated its composition, explored the theories, but the story of 55 Cancri E is far from over. In fact, we're still at the beginning. Let's talk about what comes next. What new technologies, what new missions, what new discoveries lie ahead that might finally solve the mystery of the diamond planet. First, there's the James Webb Space Telescope, which I mentioned earlier. JWST is already revolutionizing exoplanet science, and its observations of 55 Cancri E are eagerly anticipated. JWST's infrared instruments can detect incredibly faint signals. When observing 55 Cancri E, it will measure the planet's thermal emission, the infrared light the planet radiates due to its heat. This will allow astronomers to create temperature maps of the planet's surface. They'll see how temperature varies between the day side and night side, whether there are hot spots or cooler regions, how heat is distributed. Temperature patterns tell us about atmospheric dynamics. If there's efficient heat transport from day to night, it suggests winds or atmospheric circulation. If the day side is much hotter, it suggests a thin atmosphere or no atmosphere. JWST will also perform detailed spectroscopy of the planet's atmosphere. It might detect new molecules beyond what Hubble found. Carbon monoxide, carbon dioxide, sulfur compounds, each would provide clues about the planet's chemistry and interior composition. And here's something particularly exciting. JWST might be able to detect signs of volcanic activity. If 55 Cancri E has active volcanoes, and there's reason to think it might, given the tidal heating from its close orbit, those volcanoes would release gases into the atmosphere. JWST might detect sudden changes in atmospheric composition, spikes in certain molecules, temperature anomalies, all signs of an eruption. Detecting active geology on an exoplanet would be a major milestone. It would tell us the planet's interior is still hot and active, that there are dynamic processes occurring beneath the surface. And the composition of volcanic gases would directly reflect the interior chemistry. If the planet is truly carbon-rich, volcanic eruptions might release carbon-based gases rather than the sulfur and water vapor we see in Earth's volcanoes. So JWST's observations expected within the next few years could significantly advance our understanding of 55 Cancri E. But JWST is just one telescope. There are others coming. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, about 15 times the size of the largest optical telescopes today. When it begins operations in the late 2020s, it will be powerful enough to directly image some exoplanets and study their atmospheres in detail. The 30-meter telescope, planned for Hawaii, and the giant Magellan telescope, also in Chile, are similarly ambitious projects. Together, these ground-based observatories will push the limits of what we can observe. They won't be able to directly image 55 Cancri E. It's too close to its star and too faint. But they'll be able to study similar planets around other stars, building up a statistical sample of carbon-rich worlds. And eventually, perhaps in the 2030s or 2040s, NASA or ESA might launch a mission specifically designed to directly image small, rocky exoplanets. Concepts like the Habitable Exoplanet Observatory, or HABEX, envision a space telescope paired with a starshade. The starshade would be a large, flower-shaped screen flown tens of thousands of kilometers in front of the telescope, blocking the star's light and allowing planets to be imaged. Such a mission could potentially image 55 Cancri A. We'd see it as a handful of pixels, not a detailed map, but enough to measure surface properties. Is it reflective or dark? Does it have bright regions and dark regions? How does its appearance change as it rotates? Even a few pixels would be revolutionary. It would transform 55 Cancri E from an abstract collection of measurements into a visible world. But there's another approach that might yield even more information. Sending a probe. Now, before you get too excited, let me be clear. Sending a spacecraft to 55 Cancri E with current technology is impossible. At 40 light years, it's far beyond our reach. Our fastest spacecraft, Voyager 1, would take about 700,000 years to travel that distance. But there are concepts for future propulsion systems that could change this. One idea is the Breakthrough Starshot Initiative, proposed by physicist Stephen Hawking and funded by entrepreneur Yuri Milner. The concept is to build tiny spacecraft, small as a postage stamp, equipped with light sails. Powerful lasers on Earth would blast these sails with light, accelerating the spacecraft to a significant fraction of light speed, perhaps 20% the speed of light. At that velocity, a probe could reach a nearby star system in just a few decades. The probes would be tiny, with minimal instruments. They couldn't slow down when they arrive. They'd zip past their target at enormous speed. But in that brief flyby, lasting just hours, they could take photographs, measure magnetic fields, sample any dust or particles in the system. Breakthrough Starshot is targeting Alpha Centauri, the closest star system to Earth, as a first destination. But if the technology proves successful, it could be scaled up to reach other nearby stars, including 55 Cancri. Imagine it, a fleet of tiny probes, each the size of a microchip, hurtling toward the diamond planet at 20% light speed. 40 years after launch they arrive. Cameras activate. Sensors turn on. For a brief moment, as they streak past at 60,000 kilometers per second, they capture images of 55 Cancri A. Those images would take another 40 years to travel back to Earth as radio signals. But eventually, 80 years after launch, humanity would receive the first close-up photographs of a carbon planet. It's a long-term project, to put it mildly. But it's not impossible. With sufficient investment and development, we could do it within this century. And the scientific payoff would be immense. Direct observations would settle many of the questions we've been debating. Is the planet truly carbon-rich? What does the surface look like? Is there volcanic activity? What's in the atmosphere? But even without sending probes, there's another avenue of research that's advancing rapidly: laboratory experiments. Scientists are using advanced equipment, diamond anvil cells, shock compression devices, powerful lasers, to recreate the extreme conditions inside super-Earths. They're studying how carbon behaves at pressures of hundreds of gigapascals and temperatures of thousands of degrees. They're investigating exotic high-pressure forms of carbon beyond ordinary diamond. They're measuring how carbon conducts electricity and heat under these conditions. Every experiment refines our models. Every new data point helps us understand what might be happening inside 55 Cancri A. In recent years, researchers have created superionic ice, a bizarre state of water where oxygen atoms are locked in a crystalline lattice while hydrogen atoms flow freely, like a liquid. This form of ice exists in the interiors of ice giant planets like Uranus and Neptune. Could there be similarly exotic forms of carbon in super-Earths? Phases that don't exist on Earth, but emerge under extreme conditions? Laboratory experiments are trying to find out. And here's where it gets really interesting. If we discover new high-pressure forms of carbon in the lab, we can then look for spectroscopic signatures of those materials in exoplanet atmospheres. Maybe there's a specific wavelength of light that only a particular carbon phase absorbs. If we detect that signature in 55 Cancri-A's atmosphere, coming from volcanic gases released from the interior, we'd have direct evidence of that exotic carbon phase inside the planet. This interplay between laboratory work and astronomical observation is how science advances. Theory predicts what should exist. Lab experiments test whether it can exist. Observations determine whether it does exist in nature. For 55 Cancri E, we're in the middle of this process. We have theories about carbon planets. We're starting to test them in labs, and we're gathering observations to see if they match reality. Over the next decade, this process will accelerate. JWST will provide new observations. Laboratory experiments will discover new materials. Computer models will become more sophisticated. Piece by piece, the puzzle will come together. But here's the beautiful thing. Even as we solve the mystery of 55 Cancri E, we'll discover new mysteries. We'll find other carbon planets with different characteristics. We'll encounter worlds that don't fit any of our current categories. The universe is endlessly complex. Every answer generates new questions. That's not a flaw in science, it's a feature. It means we'll never run out of things to investigate. And who knows what we'll find? Maybe there's a carbon planet with a thick atmosphere and moderate temperatures, where complex organic chemistry occurs. Maybe there's a carbon moon orbiting a gas giant, with cryovolcanoes erupting liquid hydrocarbons. Maybe, somewhere out there, there's a carbon planet where life has found a way to exist using chemistry we've never imagined. The possibilities are limitless, and the only way to find out what's real is to keep looking, keep studying, keep exploring. That's the future of discovery. Not a single moment of revelation, but an ongoing process of learning. A journey without end, always moving forward, always revealing new wonders. And we get to be part of it. Right now, in this moment, we're living through the golden age of exoplanet discovery. Future generations will look back at this era with the same awe we feel when we read about Galileo discovering Jupiter's moons, or Hubble discovering the expansion of the universe. We're the generation that learned planets are common, that discovered worlds made of diamond, that found thousands of planetary systems, each one unique. That's an extraordinary privilege, and it's a responsibility, because the discoveries we make today will shape how humanity sees itself and its place in the cosmos for centuries to come. Now we reach the heart of it all, the revelation that ties everything together, the implication that changes everything. We've talked about how 55 Cancri might be a diamond planet. We've explored the physics, the chemistry, the formation scenarios. We've marveled at the idea of a world made of crystalline carbon. But here's what we haven't fully addressed. What does this mean for the universe as a whole? Let me take you on a journey through time, deep time, cosmic time. The universe began 13.8 billion years ago with the Big Bang. In those first moments, only the lightest elements existed, hydrogen and helium, with trace amounts of lithium. Nothing else. For hundreds of millions of years, the universe was dark. No stars, no planets, no complex chemistry. Just clouds of hydrogen and helium, slowly collapsing under gravity. Then the first stars ignited, massive, short-lived, burning through their fuel in just a few million years. And when they died, they exploded as supernovae, scattering newly formed elements into space. Those elements, carbon, oxygen, nitrogen, iron, silicon, all the building blocks of planets and life, mixed with primordial, hydrogen, and helium. When the next generation of stars formed, they had these heavier elements available, and some of those stars formed planets. The earliest planets were probably simple, mostly hydrogen and helium, like Jupiter. But as generations of stars lived and died, each one enriching the interstellar medium with heavier elements, planets became more complex. Rocky planets formed, water worlds, eventually planets with atmospheres and oceans, and on at least one world, life. This process, stars creating elements, scattering them in supernovae, those elements forming new planets, has been ongoing for over 13 billion years. And it's still happening now. Right now, stars are dying and new ones are being born. New planets are forming around young stars. The universe is still creating worlds. But here's the key insight. The composition of planets depends on when and where they form. Early in the universe's history, there weren't many heavy elements available. Planets forming in that era would be different from planets forming today because the raw materials were different, and the ratio of elements varies depending on the history of the region. A region near many supernovae will be enriched in certain elements. A region far from stellar activity will have fewer heavy elements. This means planetary diversity isn't random. It's a consequence of cosmic history. Every planet is a product of the specific mix of elements available in its birth environment, which in turn is a product of all the stars that lived and died before it. 55 Cancri E is carbon-rich, because the region where it formed had an unusual carbon to oxygen ratio. And that ratio existed because of the specific history of stellar evolution in that region. In other words, the diamond planet is a fossil. It's a record of stellar alchemy, a snapshot of cosmic chemistry frozen in planetary form. And here's where it gets profound. Every planet is a fossil. Every world tells a story about the universe's history. Earth, with its iron core and silicate mantle, tells the story of a protoplanetary disk enriched in oxygen and silicon. Mars's iron oxide surface tells of water that once flowed and a magnetic field that died. The gas giants tell of formation in the cold outer disk where ices could condense. We can read these stories. We can look at a planet's composition and work backward to understand the conditions that created it. This transforms planetary science from descriptive to historical. We're not just cataloging worlds, we're reconstructing the history of the cosmos. And carbon planets like 55 Cancri E are a crucial part of that story. They tell us about carbon-rich environments, about the conditions that create unusual elemental ratios, about the diversity of outcomes in planetary formation. But there's something even bigger at play here. The universe is evolving, not in a biological sense, but in a chemical sense. With each generation of stars, the universe becomes more enriched in heavy elements. The first stars had no planets. The next generation had gas giants. Later generations had rocky planets. Eventually, planets with water and organic chemistry. And now, perhaps, we're at a stage where diamond planets can form, where the specific conditions, sufficient carbon, sufficient pressure, the right stellar environment, align to create these exotic worlds. What does this mean for the future? Billions of years from now, when the sun has died and Earth is long gone, new stars will form from the enriched material of our solar system. Those stars might have planets with even more diverse chemistry, because they'll have access to elements and ratios that don't exist in our region today. The universe is becoming more complex, more diverse, more interesting. And life, if it's common, if it emerges wherever conditions allow, is part of this process. Life takes simple elements and organizes them into complex structures. It creates order from disorder. It accelerates the universe's tendency toward complexity. Some scientists think life might be inevitable. Not specific life forms, but life as a principle. A process that emerges whenever matter becomes complex enough, wherever energy flows through a system in the right way. If that's true, then the universe is becoming more alive. As it ages, as it becomes chemically richer, it creates more opportunities for life to emerge. And perhaps, on some carbon-rich world around some distant star, in some future era we can barely imagine, life will arise using chemistry we never predicted. Life that incorporates the very diamond in the planet's crust, that uses carbon in ways we've never conceived, that represents an entirely new branch of biology. We won't be here to see it, but it might happen nonetheless. This is the grandest implication of the diamond planet. It's not just a curiosity, not just an astronomical oddity. It's evidence of the universe's creative potential. It's proof that matter can organize itself in more ways than we ever imagined. And if matter can create a planet of diamond, what else is possible? Could there be planets with cores of metallic hydrogen compressed into a state that doesn't exist anywhere in our solar system? Could there be worlds where exotic matter from neutron star mergers has been incorporated, creating chemistry unlike anything we've studied? Could there be places where the fabric of space-time itself is warped by nearby black holes or other extreme objects, creating conditions that don't exist anywhere else? The universe is vast. It contains quadrillions of planets, maybe more, and each one is an experiment in what matter can become under different conditions. We've barely begun to catalogue that diversity. We've found a few thousand exoplanets out of quadrillions. We've studied a handful in detail. We've directly imaged maybe a dozen. We're standing at the edge of an ocean, having examined a few drops of water, trying to understand the whole. And yet, from those few drops, we've learned that the ocean is stranger, deeper, more wondrous than we ever dreamed. That's the real revelation. Not that one planet is made of diamond, but that the universe is endlessly creative. That matter, following simple physical laws, can create infinite complexity. That we live in a cosmos where the impossible becomes real. Every new discovery hammers this home. Every strange planet, every unexpected observation, every theory that turns out to be true despite seeming absurd. The universe doesn't care about our intuitions. It doesn't limit itself to what seems reasonable. It simply is in all its strange glory. And we, tiny creatures on a small planet, get to discover this. We get to peer into the darkness and find diamond worlds, carbon chemistry, exotic matter. We get to understand, little by little, the true nature of reality. That's the privilege of being human in the 21st century. That's the gift of science. That's what the diamond planet represents. Not wealth, not resources, but knowledge, understanding, wonder. The universe is showing us what it can do, and the diamond planet is just one small example, one tiny hint of the creativity embedded in physical law. Imagine what else is out there, waiting to be found. What other impossible worlds exist in the darkness? We don't know, not yet, but we're going to find out.